Hey everyone, and welcome to this Python and OpenCV course. In this course, we'll be talking about everything you need to know to get started with OpenCV and Python. We're going to start off with the very basics, that is reading in images and video, manipulating those media files with image transformations, and how to draw shapes and put text on those files. Then we're going to move on to the more advanced parts of OpenCV, that is switching between color spaces, bitwise operators, masking, histograms, edge detection, and thresholding. And finally, to sum things up, we'll be talking about face detection and face recognition in OpenCV, so how to detect and find faces in an image, and how to recognize them using inbuilt methods. In the last video, we'll be building a deep computer vision model to classify between the characters in The Simpsons based off some images. All material discussed will be available on my GitHub page, and all relevant links will be put up in the description below. So if that sounds exciting, don't forget to head over and subscribe to my channel, and I'll see you in the course. Hey everybody, and welcome to this Python and OpenCV course. Over the next couple of videos, we're going to be talking about using the OpenCV library to perform all sorts of image and video related processing and manipulations. Now, I won't be delving into what OpenCV really is, but just to be brief, it is a computer vision library that is available in Python, C++, and Java. Now, computer vision is an application of deep learning that primarily focuses on deriving insights from media files, that is, images and video. Now, I'm going to assume that you already have Python installed on your system, and a good way to check this is by going to your terminal and typing python --version. Now make sure you're running a version of Python of at least 3.7 above. Whatever we do in this course won't really work in some older versions of Python, and especially Python 2. So just make sure that you have the latest version installed. Go ahead to python.org and download the latest version from there. Now, assuming that you've done this, we can proceed to installing the packages that we require in this course. The first one is OpenCV. So go ahead and do a pip install OpenCV-contrib-python. Now, sometimes you may find people telling you to install just OpenCV-python. Well, this OpenCV-python is basically the main package, the main module of OpenCV. OpenCV-contrib-python includes everything in the main module as well as the contribution modules provided by the community. So this is something I recommend you install, as it includes all of OpenCV's functionality. Now, you may also notice that OpenCV tried to install the NumPy package. Now, NumPy is kind of a scientific computing package in Python that's extensively used in matrix and array manipulations, transformations, reshaping, and things like that. Now, we'll be using NumPy in some of the videos in this course, but don't worry if you've never used them before. It's simple and relatively easy to get started with. Now, the next package I'd like you to install is Sierra. So go ahead and do a pip install Sierra. Now, slight disclaimer, this is a package that I built to basically help you to speed up your workflow. Sierra is basically a set of utility functions that will prove super useful to you in your computer vision journey. It has a ton of super useful, helpful functions that will help speed up your workflow. Now, although we're not going to be using this for a good part of this course, in fact, we'll only begin to use this in the last video of this course when we're building a deep computer vision model, I recommend you install it now so that you don't have to worry about the installation process later on. If you're interested in contributing to this package, or just simply want to explore the codebase, I'll leave a link to this GitHub page in the description below. Okay, that's it for this video. In the next video, we'll be talking about how to read images and video in OpenCV. So I'll see you guys in the next video. Hey everybody, and welcome back to another video. In this video, we're going to be talking about how to read images and video in OpenCV. So I have a bunch of images in this photos folder and a couple of videos in this videos folder. In the first half of this video, we'll be talking about how to read in images in OpenCV, and towards the end, we'll be actually talking about how to read in videos. So let's start off by creating a new file and call this read.py. And the first thing we have to do is actually import cv2 as cv. So the way we read in images in OpenCV is by making use of the cv.imread method. Now this method basically takes in a path to an image and returns that image as a matrix of pixels. Specifically, we're going to be trying to read this image of a cat here. So we're going to say photos/cat.jpg, and we're going to capture this image in a variable called img. Now you can also provide absolute paths, but since this photos folder is inside my current working directory, I'm going to reference those images relatively. Now once we've read in our image, we can actually display this image by using the cv.imshow method. Now this method basically displays the image as a new window. So the two parameters we need to pass into this method is actually the name of the window, in this case it's going to be cat, and the actual matrix of pixels to display, which in this case is img. And before we actually move ahead, I do want to add an additional line, a cv.waitKey0. Now the cv.waitKey0 is basically a keyboard binding function. It waits for a specific delay or time in milliseconds for a key to be pressed. So if you pass in 0, it basically waits for an infinite amount of time for a keyboard key to be pressed. Don't worry too much about this, it's not really that important for this course, but we will be discussing some parts of it towards the end of this video. So let's actually save this and run by saying python read.py, and the image is displayed in a new window. Cool. Now this was a small image. This was an image of size 640 by 427. Now we're going to try and read in this image of the same cat, but a much larger version, a 2400 by 1600 image. So we're going to say cat_large.jpg. Let's save that and run. And as you can see, this image goes way off screen. The reason for this is because the dimensions of this image were far greater than the dimensions of the monitor that I'm currently working on. Now currently, OpenCV does not have an inbuilt way of dealing with images that are far greater than your computer screen. There are ways to mitigate this issue, and we'll be discussing them in the next video when we talk about resizing and rescaling frames and images. But for now, just know that if you have large images, it's possibly going to go off screen. So that's it for reading images. We can now move on to reading videos in OpenCV. So let's go reading videos. So what we're going to do is we're actually going to read in this video of a dog. And the way we read in videos is by actually creating a capture variable and setting this equal to cv.video capture. Now this method either takes in integer arguments like 0, 1, 2, 3, etc., or a path to a video file. Now you would provide an integer argument like 0, 1, 2, and 3 if you are using your webcam or a camera that is connected to your computer. In most cases, your webcam would be referenced by using the integer 0, but if you have multiple cameras connected to your computer, you could reference them by using the appropriate argument. For example, 0 would reference your webcam, 1 would reference the first camera that is connected to your computer, 2 would reference the second camera, and so on. But in this video, we'll be actually looking at how to read in already existing videos from a file path. Now, specifically, we'll be reading this video of a dog here, and the way we do that is by providing the path. So videos/dog.mp4. Now, here's where reading videos is kind of like different from reading images. In the case of reading in videos, we actually use a while loop and read the video frame by frame. So we're going to say while true, and the first thing we want to do inside this loop is say is true and frame is equal to capture.read. Now this capture.read basically reads in this video frame by frame. It returns the frame and a boolean that says whether the frame was successfully read in or not. To display this video, we can actually display an individual frame. So we do this by saying cv.imshow, and we call this video, and we pass in the frame. And finally, for some way to stop the video from playing indefinitely is by saying if cv.waitKey20 and 0xff is equal to odd of d, then we want to break out of this while loop. And once that's done, we can actually release the capture pointer and we can destroy all windows. And we can get rid of this. So basically, just to recap, the capture variable is an instance of this video capture class. Inside of while loop, we grab the video frame by frame by utilizing the capture.read method. We display each frame of the video by using the cv.imshow method. And finally, for some way to break out of this while loop, we say if cv.waitKey20 if and 0xff is equal to odd of d, which basically says that if the letter D is pressed, then break out of this loop and stop displaying the video. And finally, we release the capture device and we destroy all the windows since we don't need them anymore. So let's save that and run. And we get a video displayed in a window like this. But once that's done, you will notice that the video suddenly stops and you get this error. Most specifically, a -215 assertion failed error. Now, if you ever get an error like this, -215 assertion failed, this would mean in almost all cases is that OpenCV could not find a media file at that particular location that you specified. Now, the reason why it happened in a video is because the video ran out of frames. OpenCV could not find any more frames after the last frame in this video, so it unexpectedly broke out of the while loop by itself by raising a CV2 error. And now you can get the same error if we comment this out, we uncomment this out, and we specify a wrong path to this image. So let's say cv.waitKey0, save that and run. And we get the exact same error. This basically again says that OpenCV could not find the image or the video frame at a particular location. Basically, it could not be read in. That's what it's saying. So that's pretty much it for this video. We talked about how to read in images in OpenCV and how to read in videos using the video capture class. In the next video, we'll be talking about how to rescale and resize images and video frames in OpenCV. So see you then. Hey everyone, and welcome back. In this video, we're going to be talking about how to resize and rescale images and video frames in OpenCV. Now, we usually resize and rescale video files and images to prevent computational strain. Large media files tend to store a lot of information in it, and displaying it takes up a lot of processing needs that your computer needs to assign. So by resizing and rescaling, we're actually trying to get rid of some of that information. Rescaling a video implies modifying its height and width to a particular height and width. Generally, it's always best practice to downscale or change the width and height of your video files to a smaller value than the original dimensions. The reason for this is because, while most cameras, your webcam included, do not support going higher than its maximum capability. So for example, if your camera shoots in 720p, chances are it's not going to be able to shoot in 1080p or higher. So to rescale a video frame or an image, we can create a function called def rescale frame, and we can pass in the frame to be resized and a scale value, which by default we're going to set as 0.75. So what I'm going to do next is I'm going to say width is equal to frame.shape of one times scale. And I'm going to copy this and do the same thing for the height. Now remember, frame.shape of 1 is basically the width of your frame or your image, and frame.shape of 0 is basically the height of the image. Now, since width and height are integers, I can actually convert these floating point values to an integer by converting it to an int. And what we're going to be doing is we're going to create a variable called dimensions and set this equal to a tuple of width, height. And we can actually return cv.resize the frame, the dimensions, and we can pass in an interpolations of cv.inter_area. Now we'll be talking about cv.resize in an upcoming video, but for now just note that it resizes the frame to a particular dimension. So that's all our function does. It takes in the frame and it scales that frame by a particular scale value, which by default is 0.75. So let's actually try to see this in action. Let's go back to this read.py and grab this code. And we can paste that there. We don't need images for now. And I'll comment these out. Now what I'm going to do is after I read in the frame, I'm going to create a new frame called frame_resized and set this equal to rescale frame of the frame, and let's leave the scale value as 0.75. And we can actually display this video resized by passing in the frame_resized. Resized. So let's save that and run python rescale.py. That was an error. Okay, we don't need this, so let's close that out. Save that and run. And this was our original video, and this is actually a resized video. The video resized by 0.75 or 75%. We can modify this by changing the scale value to maybe 0.2. So we're rescaling it to 20%. And we get an even smaller video in a new window. So let's close that out. Now you can also apply this on images. So let's uncomment that out, change that to cat.jpg, and we can do a cv.imshow image and pass in the resized image, and we can create a resized image by calling rescale frame, and we could pass in the img. So let's save that and run. And this is our small videos. We're not concerned with that. This is actually the big image, the large image, and this is the resized version of this image. So let's close that out. Now there is another way of rescaling or resizing video frames specifically, and that's by actually using the capture.set method. Now this is specifically for videos and won't work for images. So let's go ahead and try to do that. Let's call this def change res. So we're changing the resolution of the image of the video. And we can pass in a width and a height. And what we're going to do is we're going to say capture.set 3, width. And we're going to do the same thing with capture.set 4, height. Now 3 and 4 basically stand for the properties of this capture class. So 3 references the width and 4 references the height. You can also expand this to maybe change the brightness in the image, and I think you can reference that by setting this to 10. But for now we're going to be interested in the width and the height. Now, I do want to point out this. This method will work for images, videos, and live video. Basically for everything you can use this rescale frame method. But the changeRes function only works for live video. That is video you read in from an external camera or your webcam, for instance. So video that is going on currently. This is not going to work on standalone video files that already exist. It just doesn't work. So if you're trying to change the resolution of live video, then go with this function. If you're trying to change the resolution of an already existing video, then go with this function. So that's pretty much it for this video. So we talked about how to resize and rescale video frames and images in OpenCV. In the next video, we'll be talking about how to draw shapes and write text on an image. So if that's everything, I'll see you guys in the next video. Hey everyone, and welcome back to another video. In this video, we're going to be talking about how to draw and write on images. So go ahead and create a new file and call this draw.py. We're going to import CV2 and CV. We're going to import the NumPy package that OpenCV had installed previously, and we're going to import that as np. We will read in an image by saying img is equal to cv.imread, pass in photos/cat.jpg. We can display that image in a new window, and we can do cv.weight key 0. Now there are two ways we can draw on images: by actually drawing on standalone images like this image of a cat here, or we can create a dummy image or a blank image to work with. And the way in which we can create a blank image is by saying blank is equal to np.zeros of shape 500 by 500 and give it a data type of uint8. uint8 is basically an image, the data type of an image. So if you want to try and see this image, see what this image looks like, we can say blank and we can pass in blank. Save that and run. Python draw.py. And this is basically the blank image that you can draw on. So we're going to be using that instead of drawing on this cat image. But feel free to use this cat image if you'd like. So the first thing we're going to do is try to paint the image a certain color. And the way we do this is by saying blank and reference all the pixels and set this equal to 0,255,0. So by painting the entire image green. And we can display this image by saying green and pass in the blank image. Save that and run. Can I broadcast? Okay, you need to give it a shape of 3. Basically, we are giving it a shape of height, width, and the number of color channels. So just keep that in mind. Save that. And this is the green image that we get. Cool. We could even change this and try to change this to red. 0,255. Save that. And we get a red image over here. Now, you can also color a certain portion of the image by basically giving it a range of pixels. So we can say 200 to 300, and then from 300 to 400. Save that and run. And you got a red square in this image. The next thing we're going to do is we're going to draw a rectangle. And the way we do this is by using the cv.rectangle method. Now this method takes in an image to draw the rectangle over, which in this case is blank, and it takes in 0.1, 0.2, color, thickness, and a line type if you like. So the 0.1 will specifically be 0,0, which is the origin, and we can go all the way across to 250, 250. Let's give it a color of 0,255,0, which is green. Give it a thickness of, let's say, 2, which is basically saying the thickness of the borders. And once that's done, we can display this image by saying, let's call this rectangle, and pass in the blank image. We can comment this out since we don't need this anymore. And we get a green rectangle that goes all the way from the origin to 250, 250. We can play around with it if you like, so we could go from 250 to maybe 500. And it goes all the way across the image. So you basically divide the image in half. Now there is a way of filling in this image a certain color, and the way we do this is instead of saying thickness is equal to 2, we say thickness is equal to cv.filled. And that basically fills in the rectangle to get this green rectangle. Now, alternatively, you can also specify this as -1. And we get the same result. What we could also do is, instead of giving it fixed values like 250 and 500, what we could do is we could say img.shape of 0, of 1 divided by 2, and image.shape of 0 divided by 2. Let's save that and run. Image is not defined. God, this is blank, and this is blank. Save that and run. And we get a nice little rectangle, or square, if you will, in this image. What it basically did is it scaled the rectangle from, instead of being this entire square, this rectangle basically has dimensions half of that of the original image. So moving on, let's try and draw a circle. Draw a circle. This is also fairly straightforward. We do a cv.circle and we pass in the blank image and we give it a center, which are basically the coordinates of the center. For now, let's set this to the midpoint of this image by saying 250, 250. Alternatively, you could also get this. Let's give it a radius of 40 pixels, give it a color of 0,0,255, which is red, BGR, and give it a thickness of, let's say, 3. We can display this image saying circle is equal to blank. And we get a nice little circle over here that has its center at 250, 250 and a radius of 40 pixels. Again, you could also fill in this image by giving a thickness of -1. And we get a nice little dot here in the middle. Cool. Now there's something else that I forgot, and that is how to draw a line, a standalone line on the image. That again is fairly straightforward. Say draw a line. We use a cv.line method, and this takes in the image to draw the line on and 2 points. Let's just copy these points, basically everything. And this basically draws a point from 0,0 to half these image dimensions, so that's 250, 250, and then it draws a line of color 0,255, 0. Let's set this to full white, so 255, 255, and 255, and basically the thickness you can specify as 3. And we didn't display this image. cv.im show, call this line, draw the line. Blank image. And we get a line that goes all across from 0,0 to 250, 250. Let's try and play around with this, and let's draw a line from 100 to maybe 250, and then it goes all the way to 300 to 400. Save that, run, and you get a line that goes from 100 to 100 to 300, 400. Cool. And finally, the last thing that we will discuss in this video is how to write text on an image. So that's write text on an image. Now the way we do this is very straightforward. We do a cv.put text, and this will put text on the blank image. We specify what we want to put on. So let's say hello. We can give it an origin, which is basically where do we want to draw the image from. Let's set this to 225 and 225. And we can also specify font face. Now OpenCV comes with inbuilt font faces, and we will be using the cv.font_Hershey_. We'll be using the XXX. You have complex, you have duplex, you have plain, you have script simplex, and a lot of inbuilt fonts. But for now, let's use the XXX. Let's give this a font scale, which is basically how much do you want to scale the font by. Let's set this to 1.0. We don't want to scale the font. Let's give it a color of 0,255,0 and give it a thickness of 2. Let's comment that out, and we can display this image. So you can see I'm show. Let's call this text and pass in the blank image. And we get some text that is placed on the image. You can play around with it and say, hello, my name is Jason. Save that and run. And it goes off screen, like when we're dealing with large images, but there's no way of actually handling this except for maybe changing the margins here a bit. So we can do that by saying, let's say 0,225. And it starts from 0 and it says, hello, my name is Jason. So that's it for this video. We talked about how to draw shapes, how to draw lines, rectangles, circles, and how to write text on an image. Now in the next video, we'll be talking about basic functions in OpenCV that you're most likely going to come across whatever project in computer vision you end up doing. So if that's it, I'll see you guys in the next video. Hey everyone, and welcome back to another video. In this video, we're going to be talking about the most basic functions in OpenCV that you're going to come across in whatever computer vision project you end up building. So let's start off with the first function, and that is converting an image to grayscale. So we've written an image and we've displayed that image in a new window. And currently this is a BGR image, a 3-channel blue, green and red image. Now there are ways in OpenCV to essentially convert those BGR images to grayscale so that you only see the intensity distribution of pixels rather than the color itself. So the way we do that is by saying gray is equal to cv.cvt color. We pass in the image that we want to convert from, which is IMG, and we specify a color code. Now this color code is cv.color_BGR to gray, since we're converting a BGR image to a grayscale image. And we can go ahead and display this image by saying cv.imshow, pass in gray, and pass in the gray image. Save that and run. We do python basic.py. And this was the original image, and this is the grayscale image. Let's try this with another image. Let's try it with this image of a park in Boston. Save that, maybe change that to Boston. And this is the BGR image in OpenCV, and this is its corresponding grayscale image. So nothing too fancy, we've just converted from a BGR image to a grayscale image. The next function that we're going to discuss is how to blur an image. Now blurring an image essentially removes some of the noise that exists in an image. For example, in an image there may be some extra elements that were there because of bad lighting when the image was taken, or maybe some issues with the camera sensor and so on. And some of the ways we can actually reduce this noise is by applying a slight blur. There are way too many blurring techniques, which we will get into in the advanced part of this course, but for now we're just going to use the Gaussian blur. So what we're going to do is we're going to create a blurred image by saying blur is equal to cv.Gaussian blur. And this image will take in a source image, which is the IMG. It will take in a kernel size, which is actually a 2x2 tuple, which is basically the window size that OpenCV uses to compute the blur on the image. We'll get into this in the advanced part of this course, so don't worry too much about this. Just know that this kernel size has to be an odd number. So let's start off real simple and keep the kernel size to 3 by 3. And another thing that we have to specify is cv.border_default. So go ahead and try to display this image by saying blur and pass in blur. Now you will be able to notice some of the differences in this image, and that is because of the blur that is applied on it, right? The people in the background are pretty clear in this image, and over here they're slightly blurred out. To increase the blur in this image, we can essentially increase the kernel size. So from 3 by 3 to 7 by 7. Save that and run. And this is the image that is way more blurred than the previous image. So that's it. The next function we're going to discuss is how to create an edge cascade, which is basically trying to find the edges that are present in the image. Now, again, there are many edge cascades that are available, but for this video, we're going to be using the Canny Edge Detector, which is pretty famous in the computer vision world. Essentially, it's a multi-step process that involves a lot of blurring and then involves a lot of gradient computations and stuff like that. So we're going to say Canny is equal to cv.canny. We pass in the image. We pass in two threshold values, which for now I'm going to say 125 and 175. Let's go ahead and try to display this image. Get the Canny edges, and we can pass in Canny. Save that and run. And these were the edges that were found in this image. As you can see that there were hardly any edges found in the sky, but a lot of features in the trees and the buildings, and quite a few, features and edges in the grass and stuff. We can reduce some of these edges by essentially blurring the image. And the way we do that is instead of passing the IMG, we pass in the blur. Save that and run. And as you can see that there were far less edges that were found in the image. And this is a way you can basically reduce the amount of edges that were found by a lot, by applying a lot of blur, or get rid of some of the edges by applying a slight blur. Now, the next function we're going to discuss is how to dilate an image using a specific structuring element. Now, the structuring element that we are going to use is actually these edges, the Canny edges that were found. So we're going to say dilating the image. And the way we do that is by saying dilated is equal to cv.dilate. And this will take in the structuring element, which is basically the Canny edges. And we'll take in a kernel size, which we'll specify as 3 by 3 for now. And it will also take in an iterations of 1. Now, dilation can be applied using several iterations at a time, but for now we're just going to stick with 1. So go ahead and try to display this image by saying cv.imshow, call this dilated, and we can pass in dilated. Save that and run. And if these were our edges, these are the dilated edges. We can maybe increase the kernel size to maybe 7 by 7 and try to see what that does. Hold on. And nothing much was done. Not much difference was there. Let's try to increase the number of iterations to maybe 3. And it's definitely way thicker, but you're going to see subtle differences with the amount of features and edges that you find. Now, there is a way of eroding this dilated image to get back this structuring element. Now, it's not going to be perfect, but it will work in some cases. So we're going to say, call this eroding, and we call this eroded is equal to cv.erode. It will take in the dilated image, pass in dilated. It will take in a kernel size of, let's start off with 3 by 3 and give it an iterations of 1, just for now. And we then display this image. And show, call this eroded. And if this was your structuring element and this was your dilated image, this is basically the result you get from eroding this image. Now, it isn't the same as a structuring element, but you can just about make the features there. But you can see that between this and this, there is a subtle change in the edges, in the thickness of these edges. We can maybe try to match these values so that there is an attempt to get back this edge cascade. And yes, we got the edges back. So as you can see that if you compare these two, they look pretty much the same. Yeah, the edges are the same. So essentially, if you follow the same steps, you can, in most cases, get back the same edge cascade. And probably the last function that we're going to discuss is how to resize and crop an image. So we're going to start with resize. So we covered resizing video frames and images in the previous video, in one of the previous videos. But we're just going to touch on the cv.resize function just a bit. So we're going to say resized is equal to cv.resize. This will take in an image to be resized, and it will take in a destination size, which let's set this to 500 by 500. And so this essentially takes in this image of the park and resizes that image to 500 by 500, ignoring the aspect ratio. So we display this image by saying cv.imshow resized and resized. Save that and run. And let's go back to this image. If this is the original image, this is the image that was resized to 500 by 500. Now by default, there is an interpolation that occurs in the background, and that is cv.inter_area. Now this interpolation method is useful if you are shrinking the image to dimensions that are smaller than that of the original dimensions. But in some cases, if you are trying to enlarge the image and scale the image to a much larger dimensions, you would probably use the inter_linear or the inter_cubic. Now, cubic is the slowest among them all, but the resulting image that you get is of a much higher quality than the inter_area or the inter_linear. So let's touch on cropping, and that's basically by utilizing the fact that images are arrays, and we can employ something called array slicing. We can select a portion of the image on the basis of their pixel values. So we can say cropped is equal to the image, and we can select a region from 50 to 200 and from 200 to 400. And we can display this image, call this cropped, pass in cropped. And this is a cropped image of, let's go back here, of this original image. If you try to superimpose them, it's probably going to be right over there. Yeah, it's basically this portion. So that's pretty much it for this video. We talked about the most basic functions in OpenCV. We talked about converting an image to grayscale by applying some blur, by creating an edge cascade, by dilating the image, by eroding that dilated image, by resizing an image, and trying to crop an image using array slicing. In the next video, we're going to be talking about image transformations in OpenCV. That's translation, rotation, resizing, flipping, and cropping. So if you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back to this Python and OpenCV course. In this section, we're going to cover basic image transformations. Now these are common techniques that you'll likely apply to images, including translation, rotation, resizing, flipping, and cropping. So let's start off with translation. Translation is basically shifting an image along the X and Y axis. So using translation, you can shift an image up, down, left, right, or with any combination of the above. So So to translate an image, we can create a translating function. We're going to call this def translate. And this translation function will take in an image to translate and take in x and y. X and y basically stand for the number of pixels you want to shift along the x-axis and the y-axis respectively. So to translate an image, we need to create a translation matrix. So we're going to call this transmet is equal to np.float32, and this will take in a list with two lists inside of it. In the first list, we're going to say 1, 0, x and 0, 1, y. And since we're using NumPy, we can import NumPy as np. And once we've created a translation matrix, we can essentially get the dimensions of the image, saying dimensions, which is a tuple of image.shape of 1, which is the width, and image.shape of 0, which is the height. And we can return cv.warp_affine. This will take in the image matrix, so transmit, and it will take in the dimensions. And with that done, we can essentially translate our image. Now, before we do that, I do want to mention that if you have negative values for x, you are essentially translating the image to the left. Negative y values imply shifting it up. Positive x values imply shifting it to the right. And as you guessed, positive y values shifted down. So let's create our first translated image. By setting this equal to translate, we're going to pass in the image, and we're going to shift the image right by 100 pixels and down by 100 pixels. So that's to a cv.imshow translated and translate. Tip. Save that and run python transformations.py. And this is your translated image. It was shifted down by 100 pixels and shifted to the right by 100 pixels. So let's change that. Let's shift the image left by 100 pixels and down by 100 pixels. So we pass in negative values for x. And it moved to the left. Feel free to play around with these values as you see fit. Just know that negative x shifts it to the left, negative y shifts it up, x shifts it to the right, and positive y values shift it down. Moving on, let's talk about rotation. Rotation is exactly what it sounds like, rotating an image by some angle. OpenCV allows you to specify any point, any rotation point that you like to rotate the image around. Usually it's the center, but with OpenCV you can specify any arbitrary point. It could be any corner, it could be 10 pixels to the right, 40 pixels down, and you can shift the image around that point. So to rotate the image, we can create a rotating function. It's called devRotate. This will take an image angle to rotate around and a rotation point, which we're going to set as none. So we're going to grab the height and the width of the image by setting this equal to ing.shape of the first two values. And basically, if the rotation point is none, we are going to assume that we want to rotate around the center. So we're going to say rot point is equal to width divided by 2 and height divided by 2. And we can essentially create the rotation matrix like we did with the translation matrix by setting this equal to rotmet is equal to cv.getRotation matrix 2D. We're going to pass in the center, the rotation point, an angle to rotate around, which is angle, and a scale value. Now we're not interested in scaling the image when we rotate it, so we can set this to 1.0. Finally, we can set a dimensions variable equal to the width and then the height. And we can return the rotated image, which is cv.warp affine image rot met the destination size, which is dimensions, and that's it. That's all we need for this function. So we can create a rotated image by setting this equal to rotate, and we can rotate the original image by 45 degrees. So let's display this image, call this rotated and pass in rotated. Save that and run. And this is your rotated image. As you can see, it was rotated counterclockwise by 45 degrees. If somehow you wanted to rotate this image clockwise, just specify negative values for this angle, and it will rotate the image around. Rotated clockwise. Now, you can also rotate a rotated image. That is, take this image and rotate it by 45 degrees further. So let's call this rotated. Rotated is equal to rotate of rotated. And we can rotate this image by another 45 degrees. So we're rotating it clockwise. And we can cv.imshow, call this rotated, and we can pass in rotated. A lot of rotateds. And this is your rotated image. Now the reason why these black lines were included is because if there's no image in it, if there's no part of the image in it, it's going to be black by default. So when you took this image and rotated it by 45 degrees, you essentially rotated the image but introduced these black triangles. Now if you try to rotate this image further by some angle, you are also trying to rotate these black triangles along with it. So that's why you get these kind of a skewed image. So those additional triangles were included over here. But save yourselves the trouble and basically add up these angles and you'll get the final angle. So we can change that to 90 and rotate the original image by -90. And this is essentially the image that we were trying to go for. Take this image, rotate it 45 degrees clockwise, and rotate this 45 degrees image by a further 45 degrees. Save yourself the trouble and add those two angle values. So far we've covered two image transformations, translation and rotation. Now we're going to explore how to resize an image. Now this is nothing too different from what we've discussed previously, but let's touch on it just a bit. So resizing, and we can create a resized variable and set this equal to cv.resize. We can pass in the image to resize and a destination size of maybe 500 by 500. And by default, the interpolation is cv.inter_area. You can maybe change this to inter_linear or inter_cubic. Definitely a matter of preference depending on whether you're enlarging or shrinking the image. If you're shrinking the image, you would probably go for inter_area or stick with the default. If you're enlarging the image, you could probably use the inter_linear or the inter_cubic. Cubic is slower, but the resulting image is better. It's of a higher quality. Again, nothing too different from what we've discussed before. So we can display this image by saying resize and passing in resized. Save that, run, and we've got a resized image. Next up, we have flipping. How to flip an image. So we don't need to define a function for this. We just need to create a variable and set this equal to cv.flip. This will take in an image and a flip code. Now this flip code could either be 0, 1, or -1. 0 basically implies flipping the image vertically, that is over the x-axis. 1 specifies that you want to flip the image horizontally or over the y-axis. And -1 basically implies flipping the image both vertically as well as horizontally. So let's start off with 0, flipping it vertically. Call this imshow, call this flip, and pass in flip. Save and run. And this is the image that was flipped vertically. Let's try a horizontal flip. And we get a horizontal flip. To really see whether it was a horizontal flip, we can bring these two images together. And if they look like mirror images, then it was flipped horizontally. This is kind of a symmetric image, so it's not that obvious, but bring them together and you can maybe find out the difference. We could also try to flip the image vertically and horizontally by specifying -1 as a flip code. And the image was flipped both vertically as well as horizontally. Mirror images, but reverse mirror images. And the last method is cropping. Now we discussed cropping again, so I'm just going to touch on it. We can create a variable called cropped and set this equal to img and perform some array slicing. So 200 to 400 and 300 to 400. Save that and run. We didn't display this image. ev.im show, let's call this cropped, pass in cropped. Save and run. And this is the cropped image. If you're trying to bring this together, it's not going to be brought together. Can't even grab a hold of this. Okay. So that's pretty much it for this video. We talked about translating an image, rotating that image, resizing an image, flipping an image, and cropping those images. We are basically just covering the basics, the basic image transformations. There are, of course, way more transformations that you could possibly do with OpenCV. But just to keep this code simple and beginner friendly, I'm only covering the basic transformations. So that's it for this video. In the next video, we're going to be talking about how to identify contours in an image. So if you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back to another video. In this video, we're going to be talking about how to identify contours in OpenCV. Now, contours are basically the boundaries of objects, the line or curve that joins the continuous points along the boundary of an object. Now, from a mathematical point of view, they're not the same as edges. For the most part, you can get away with thinking of contours as edges, but from a mathematical point of view, contours and edges are two different things. Contours are useful tools when you get into shape analysis and object detection and recognition. So in this video, I sort of want to introduce you to the idea of contours and how to identify them in OpenCV. So the first thing I've done is I've written a file, an image file, and I've displayed that image using the cv.im show method. The next thing I want to do is convert this image to grayscale by saying gray is equal to cv.cvt color img cv.color underscore bgr to gray. And we can display this. So just to know that we're on the same footing, I'm going to run this. So python contours.py. And we get a gray image over here. Now after this, I want to essentially grab the edges of the image using the Canny edge detector. So I'm going to say Canny is equal to cv.canny. We're going to pass in the img and we're going to give it two threshold values. So 125 and 175. And we can display this image, calling this Canny edges, pass in Canny. Let's save that and run. Close it out. I didn't save that. Save that and run. And these are the edges that were there in the image. Now, the way we find the contours of this image is by using the find contours method. Now, this method basically returns two things: contours and hierarchies. And essentially, this is equal to cv.find contours. This takes in the edges, so Canny, and it takes in a mode in which to find the contours. Now, this is either cv.reta_tree if you want all the hierarchical contours, or the reta external if you want only the external contours, or reta list if you want all the contours in the image. The next method we pass in is actually the contour approximation method. For now, we're going to set this to cv.chain_approx_none. So let's just have a top-down look at what this function does. So essentially the cv.findContours method looks at the structuring element or the edges that were found in the image and returns true values. The contours, which is essentially a Python list of all the coordinates of the contours that were found in the image, and hierarchies, which is really out of the scope of this course, but essentially it refers to the hierarchical representation of contours. So for example, if you have a rectangle, and inside the rectangle if you have a square, and inside of that square you have a circle, so this hierarchies is essentially the representation that OpenCV uses to find these contours. This cv.reta_list essentially is a mode in which this findContours method returns and finds the contours. Reta_list essentially returns all the contours it finds in the image. We also have reta external, like we discussed. Reta external retrieves only the external contours, so all the ones on the outside, it returns those. Reta_tree returns all the hierarchical contours, so all the contours that are in a hierarchical system, that is returned by reta_tree. For now, I'm just going to set this to a list to return all the contours in the image. The next one we have is the contour approximation method. This is basically how we want to approximate the contour. So chain_approx none does nothing, it just returns all of the contours. Some people prefer to use chain_approx simple, which essentially compresses all the contours that are returned into simple ones that make the most sense. So for example, if you have a line in an image, if you use chain_approx none, you are essentially going to get all the contours, all the coordinates of the points of that line. Chain_approx simple essentially takes all of those points of that line, compresses it into the two endpoints only. Because that makes the most sense. A line is defined by only two endpoints. We don't want all the points in between. That, in a nutshell, is what this entire function is doing. So since contours is a list, we can essentially find the number of contours that were found by finding the length of this list. So we can print the length of this list. And we can say, grab that there. And we can say these many contours found. Okay, so let's save that and run. And we found 2,794 contours in the image. Now this is huge. This is a lot of contours that were found in the image. So let's do a couple of things. Let's try to change this chain_approx simple to chain_approx none and see what that does. See how that affects our length. Now there isn't any difference between those two because I'm guessing that there were no points to compress since there are a lot of edges and points in this image, so there wasn't a lot of compression. So let's change it back to simple. And actually what I want to do is I want to blur this image before I find the edges. So let's do a blur is equal to cv.gaussian blur. We can pass in the gray image and we can give it a kernel size of, let's do a lot of blur, so 5 by 5. And maybe we can give a border default of cv.border_default. And we can, if you want to, and we can display this image, call this blur, and pass in blur. And we can find the edges on this blurred image. So let's call this blur. And as you can see, the significant reduction in the number of contours that were found just by blurring the image. So it went all the way from 2794 to 380. That's close to 7 times just by blurring the image with a kernel size of 5 by 5. Okay, now there is another way of finding the contours, is that instead of using this canny edge detector, we can use another function in OpenCV, and that is thresholding. So I'm just going to comment this out, and down here what I'm going to do is I'm going to say ret thresh is equal to cv.threshold. This will take in the gray image and will take in a threshold value of 125 and a maximum value of 255. Don't worry too much about thresholding for now. Just know that thresholding essentially looks at an image and tries to binarize that image. So if a particular pixel is below 125, if the intensity of that pixel is below 125, it's going to be set to 0 or black. If it is above 125, it is set to white or 255. That's all it does. And in the find contours method, we can essentially pass in the thresh value. So let's save that. Let's close this out and try to run that. Type. Okay, threshold missing a type. Okay, I think I forgot one part. We have to specify a thresholding type. So this is cv.thresh_binary. So we're binarizing the image basically. Okay, let's run that. And there were 839 contours that were found. We can visualize that. Let's print. Let's display this thresh image. Passing in thresh. Save that and run. And this was the thresholded image. You're using 125. I'll close this out. Using 125 as our threshold value and 255 as our maximum value, we got this thresholded image. And when we try to find the contours on this image, we got 839 contours. Now, don't worry too much about this thresholding business. We'll discuss this in the advanced section of this course more in depth. Just know that thresholding attempts to binarize an image. Take an image and convert it into binary form. That is either 0 or black, or white, or 255. Now, what's cool in OpenCV is that you can actually visualize the contours that were found on the image by essentially drawing over the image. So what I'm going to do real quick is actually import numpy as np, and after this I'm going to create a blank variable and set this equal to np.zeros of image.shape of the first two values, and maybe give it a data type of, I don't know, uint8. We can display this image, call this blank, pass in blank, just to visualize and have a blank image to work with. Let's save that and go to a blank image. This is of the same dimensions as our original cat's image. So what I'm going to do is I'm going to draw these contours on that blank image so that we know what kind of contours that OpenCV found. So the way we do that is by using the cv.drawContours method. It takes in an image to draw over, so blank. It takes in the contours, which has to be a list, which is, in this case is just the contours list. It takes in a contour index, which are basically how many contours do you want in the image. Since we want all of them, since we want to draw all of them, we can specify -1. Give it a color. Let's set this to BGR, so let's set this to red, 0,0,255. And we can give it a thickness of maybe 2. And we can display the blank image. So let's call this contours drawn, and we can pass in blank. Save that and run. Okay, there was an error. I think this has to be shape. Okay, so these were the contours that were drawn on the image. If you take a look at the thresholded value, thresholded image, it's not the same thing. what I believe it attempted to do is instead it found the edges of this image, all the edges of this image, and attempted to draw it out on this blank image. So let's set this. So let's set the thickness to maybe 1, so that we have a crisper view. Oops. Okay, so these were the contours that were drawn in the image. And in fact, if you try to visualize it with Kenny, let's actually visualize that with Kenny. Uncomment that out, run. Blur is not defined. Okay, that has to be an image. Okay, let's look at Kenny. Let's look at this. Okay, it's not the same thing. And that makes sense because our find contours method didn't use Kenny as a basis of detecting and finding the contours. But we can do that. Let's not use a thresholding method, and instead let's use Kenny. So we can pass in Kenny here, save that and run. And okay, they're pretty much the same thing, right? It's basically a mirror image of these two. Like I said, you can get away with thinking of contours as edges. They're not the same thing, but you can think of them as edges because from a programming point of view, they are kind of like the edges of the image, right? They are the boundaries, they are curves that join the points along the boundary. Those are basically edges. So let's try to blur that image. Let's uncomment that out. Let's see what that does. I don't think that had any effect because we didn't pass in blur. Okay, 380 contours that were found and mirror images of each other. So generally what I recommend is that you use Kenny method first and then try to find the contours using that, rather than try to threshold the image and then find the contours on that. Because like we'll discuss in the advanced section, this type of thresholding, the simple thresholding, has its disadvantages. Maybe because we're passing in a simple, just one value, try to binarize the image using this threshold value, right? It's not the most ideal, but in some cases, in most cases, it is the most favored kind of thresholding because it's the simplest and it does the job pretty well. So that's pretty much it for this video. We talked about how to identify contours in OpenCV, but in two methods. First, trying to find the edge cascades of the image using the Kenny edge detector, and try to find the contours using that. And also trying to binarize that image using the CV.threshold and finding the contours on that. So if you have any questions, leave them in the comments below. I'll be sure to check them out. Otherwise, as always, I'll see you guys in the next video. Hey everyone, and welcome back to another video. We are now at the advanced section of this course, where we are going to discuss the advanced concepts in OpenCV. So what we're going to be doing in this video is actually discussing how to switch between color spaces in OpenCV. Now, color spaces are basically a space of colors, a system of representing an array of pixel colors. RGB is a color space, grayscale is a color space. We also have other color spaces like HSV, LAB, and many more. So let's start off with trying to convert this image to grayscale. So we're going to convert from a BGR image, which is OpenCV's default way of reading in images, and we're going to convert that to grayscale. So the way we do that is by saying gray is equal to cv.cvt color. We pass in the image and we specify a color code, which is cv.color_BGR to gray, since we're converting from a BGR image format to grayscale format. And we can display this image by saying gray and passing in gray. Let's save that and run. Python spaces.py. We had a problem, that's a comma. Save and run. And this is the grayscale version of this BGR image. Cool, pretty cool. Grayscale images basically show you the distribution of pixel intensities at particular locations of your image. So Let's start off with trying to convert this image to an HSV format. So from BGR to HSV. HSV is also called hue saturation value and is kind of based on how humans think and conceive of color. So the way we convert that is by saying HSV is equal to cv.cvt color. We pass in the img variable and we specify a color code, which is cv.color_bgr to HSV. And we can display this image, call this HSV, and pass in HSV. Let's save that. And this is the HSV version of this BGR image. As you can see, that there is a lot of green in this area and the skies are reddish. Now we also have another kind of color space, and that is called the LAB color space. So we're going to convert from BGR to LAB. This is sometimes represented as L times A times B, but feel free to use whatever you want. So LAB is equal to cv.cvt color. We pass in the img and the color_bgr to LAB. cv.imshow, call this LAB and pass in LAB. Just run that. And this is the LAB version of this BGR image. This kind of looks like a washed down version of this BGR image, but hey, that's the LAB format. It's more tuned to how humans perceive color. Now, when I started off with this course, I mentioned that OpenCV reads in images in a BGR format, that is blue, green, and red. Now, that's not the current system that we use to represent colors outside of OpenCV. Outside of OpenCV, we use the RGB format, which is kind of like the inverse of the BGR format. Now, if you try to display this IMG image in a Python library that's not OpenCV, you're probably going to see an inversion of colors. And we can do that real quick. Let's try to import matplotlib.pyplot as PLT. And we can basically comment that out. And we can try and display this image variable. So we're going to say plt.imshow, pass in the image, and we can say plt.show. Maybe let's comment this out, save that and run. And this is the image you get. Now, if you compare it with the image that OpenCV read, this is completely different. These two are completely different images. And the reason for this is because this image is a BGR image and OpenCV displays BGR images. But now if you try to take this BGR image and try to display it in matplotlib, for instance, matplotlib has no idea that this image is a BGR image and displays that image as if it were an RGB image. So that's why you see an inversion of color. So where there's red over here, you see a blue, and where there's blue over here, you see a red. And there are ways to convert this from BGR to RGB, and that is by using OpenCV itself. So let's comment that out, and let's uncomment this all out. And right over here, let's say BGR to RGB. And what we're going to say is RGB is equal to cv.cvt color. We can pass in the BGR image. Oopsie. We can pass in the BGR image. And what we're going to do is specify a color code, which is cv.color_bgr to RGB. And we can try to display this image in OpenCV and see what that displays. RGB. And we can also display this in matplotlib. So let's pass in the RGB, and we can do plt.show. Save that and go here. Oops. Let's do python spaces.py. What I'm most interested in is this and this. Now, again, you see an inversion of colors, but this time in OpenCV, because now you provided OpenCV an RGB image, and it assumed it was a BGR image, and that's why there's an inversion of colors. But we passed in the RGB image to matplotlib, and Matplotlib's default is RGB, so that's why I displayed the proper image. So just keep this in mind when you're working with multiple libraries, including OpenCV and Matplotlib, for instance, because do keep in mind the inversion of colors that tends to take place between these two libraries. So, now another thing that I want to do is we've essentially converted the BGR to grayscale. We've essentially converted BGR to HSV, BGR to LAB, BGR to RGB. What we can do is we can do the inverse of that. We can convert a grayscale image to BGR. We can convert an HSV to BGR. We can convert an LAB to BGR and RGB to BGR and so on. But here's one of the downsides. You cannot convert a grayscale image to HSV directly. If you wanted to do that, what you have to do is convert the grayscale to BGR and then from BGR to HSV. So we're going to do that real quick. So we're going to say HSV to BGR. Okay. So the first thing we do is HSV underscore BGR, basically converting from HSV to BGR, is equal to cv.cvt color. This will take in the HSV image, and the color code will be color underscore HSV to BGR. And we can display this image. Let's call this HSV to BGR and pass in HSV underscore BGR. Underscore BGR. Save that and run. Okay, we're not interested in this, so let's close this out. But essentially, this is the HSV to BGR image. If this was the HSV image, we converted this image to BGR. And we can try this with LAB. So let's call this LAB to LAB, and let's call this LAB. And let's copy this and paste that there. And we can get rid of Matplotlib since we're not interested in it anymore. Save that and run. Okay, there was a mistake. We said HSV LAB to LAB to BGR. That was my mistake. Cool. So if this was the LAB version, this is the LAB to BGR version. Back from BGR to LAB and from LAB to BGR. So that's pretty much it for this video. We discussed how to convert between color spaces from BGR to grayscale, HSV, LAB, and RGB. And if you want to convert from grayscale to LAB, for instance, note that there is no direct method. What you could do is convert that grayscale to BGR, and then from BGR to LAB. That's possible. But directly, I don't think there is a way to do that. If OpenCV could come up with a feature like that, it would be good, but it's not going to hurt you to write extra lines of code. At least 2 or 3 lines of code extra would really hurt you. In the next video, we'll be talking about how to split and merge color channels in OpenCV. If you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back to another video. In this video, we're going to be talking about how to split and merge color channels in OpenCV. Now, a color image basically consists of multiple channels: red, green, and blue. All the images you see around you, all the BGR or the RGB images, are basically these 3 color channels merged together. Now, OpenCV allows you to split an image into its respective color channels. So you can take a BGR image and split it into blue, green, and red components. So that's what we're going to be doing in this video. We're going to be taking this image of the park that we had seen in the previous videos, and we're going to split that into its 3 color channels. So the way we do that is by saying B, G, R, which stand for the respective color channels, and set this equal to cv.split of the image. So the cv.split basically splits the image into blue, green, and red. And we can display this image by saying cv.imShow. Let's call this blue and pass in blue. And let's do the same for the green image and pass in G. And we can do the same for the red part. So R. And we can actually visualize the shapes of these images. So let's first print the image.shape, and then print the b.shape, and then print the g.shape, and then print the r.shape. So basically we're printing the shapes and dimensions of the image in the blue, green, and red. And we're also displaying these images. So let's run python split merge.py. And these are the images that you get back. This is the blue image, this is the green image, and this is the red image. Now these are depicted and displayed as grayscale images that show the distribution of pixel intensities. The regions where it's lighter show that there is a far more concentration of those pixel values, and regions where it's darker represent that there are little or even no pixels in that region. So take a look at the blue channel first, and if you compare it with the original image, you will see that the sky is kind of almost white. This basically shows you that there is a high concentration of blue in the sky and not so much in the trees or the grass. Let's take a look at the green, and there is a fairly even distribution of pixel intensities between the grass, the trees, and some parts of the sky. And take a look at the red color channel, and you can see that parts of the trees that are red are whiter, and the grass and the sky are not that white in this red image. So this means that there is not much red color in those regions. Now coming back, let's take a look at the shapes of the image. Now this stands for the original image, the BGR image. The additional element in the tuple here represents the number of color channels. 3 represents 3 color channels, blue, green, and red. Now if we proceeded to display the shapes of the B, G, and R components, we don't see a 3 in the tuple. That's because the shape of that component is 1. It's not mentioned here, but it is 1. That's why when you try to display this image using cv.imshow, it displays it as a grayscale image, because grayscale images have a shape of 1. Now, let's try and merge these color channels together. So the way we do that is by saying the merged image is equal to cv.merge, and what we do is we pass in a list of blue, G, R. Let's save that and let's display that. Saying cv.imshow, call this the merged image, and we can pass in merged. So let's save that and run. And we get back the merged image by basically merging the 3 individual color channels, the red, the green, and the blue. Now, there is an additional way of looking at the actual color there is in that channel. So instead of showing you grayscale images, it shows you the actual color involved. So for the blue image, you get the blue color channel. For the red channel, you get the red color for that channel. And the way we do that is we actually have to reconstruct the image. The shapes of these images are basically grayscale images. But what we can do is we can actually create a blank image using NumPy. And essentially what we're going to do is we're going to say blank is equal to np.zeros, and we're going to set this to the shape of the image, but only the first 2 values, and we can give it a data type of uint8, which basically are for images. And to print the blue color channel, what we're going to do is we're going to say down here, we're going to say blue is equal to cv.merge. We're going to pass in a list of b, blank, blank. And we're going to do the same thing for green and set this equal to cv.merge of blank, G, blank. And we're going to do the same thing for red by setting this equal to cv.merge of blank, blank, red. Basically what I've done is this blank image basically consists of the height and the width, not necessarily the number of color channels in the image. So by essentially merging the blue image in its respective compartment, so blue, green, and red, we are setting the green and the red components to black and only displaying the blue channel. And we're doing the same thing for the green by setting the blue and the red components to black, and the same thing for red by setting the blue and the green components to black. And we can display this by saying blue, green, and red. Let's save that and run. And now you actually get the color in its respective color channels. Taking a look at this, you'll now be able to visualize the distribution much better. Here you can see lighter portions represent a high distribution. Lighter portions here represent a high distribution of red, and higher and wider regions represent a high distribution of green. So essentially, if you take these three images of these color channels and merge them together, you essentially get back the merged image. So that's that, the merged image. So that's pretty much it for this video. We discussed how to split an image into its three respective color channels, how to reconstruct the image to display the actual color involved in that channel, and how to merge those color channels back into its original image. In the next video, we'll be talking about how to smooth and blur an image using various blurring techniques. If you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back to another video. In this video, we're going to address the concepts of smoothing and blurring in OpenCV. Now, before, I mentioned that we generally smooth an image when it tends to have a lot of noise, and noise that's caused from camera sensors or basically problems in lighting when the image was taken. And we can essentially smooth out the image or reduce some of the noise by applying some blurring method. Now, previously we discussed the Gaussian blur method, which is kind of one of the most popular methods in blurring. But generally, you're going to see that Gaussian blur won't really suit some of your purposes. And that's why there are many blurring techniques that we have, and that's what we're going to address in this video. Now, before we actually do that, I do want to address a couple of concepts. Let's actually go to an image and discuss what exactly goes on when you try to apply blur. So essentially, the first thing that we need to define is something called a kernel or a window. And that is essentially this window that you draw over an image. That's two lines here. Maybe let's draw another line there. Yeah. So this is essentially a window that you draw over a specific portion of an image. And something happens on the pixels in this window. So let's change that to blue. Yeah. So essentially, this window has a size. This size is called a kernel size. Now, kernel size is basically the number of rows and the number of columns. So over here we have 3 columns and 3 rows. So the kernel size for this is 3 by 3. Now, essentially what happens here is that we have multiple methods to apply some blur. So essentially, blur is applied to the middle pixel as a result of the pixels around it, also called the surrounding pixels. Let's change that to a different color. So something happens here as a result of the pixels around, the surrounding pixels. So with that in mind, let's go back and discuss the first method of blurring, which is averaging. So essentially, averaging is we define a kernel window over a specific portion of an image. This window will essentially compute the pixel intensity of the middle pixel of the true center as the average of the surrounding pixel intensities. So if this was, let's change it to green. So suppose if this pixel intensity was 1, this was maybe 2, this is 3, 4, 5, 6, 7, 8, you get the point. Essentially, the new pixel intensity for this region will be the average of all the surrounding pixel intensity. So that's summing up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 and dividing that by 8, which is essentially the number of surrounding pixels. And we essentially use that result as a pixel intensity for the middle value or the true center. And this process happens throughout the image. So this window basically slides to the right, and once that's done, it slides down. and computes it basically for all the pixels in the image. So let's try to apply and see what this does. So what we're going to do is we're going to say average is equal to cv.blur. The cv.blur method is a method in which we can apply averaging blur. So we define the source image, which is img. We give it a kernel size of, let's say, 3 by 3, and that's it. We can display this image, call this average blur, save that and run. Python smoothing.py. Matt, gosh, we have to pass an average, save that and run. And this is basically the average blur that's applied. So what the algorithm did in the background was essentially define a kernel window of the specified size, so 3 by 3, and it computed the center value for a pixel using the average of all the surrounding pixel intensities. And the result of that is we get a blurred image. So the higher kernel size we specify, the more blur there is going to be in the image. So let's increase that to 7 by 7 and see what that does. And we get an image with way more blur. So let's move on to the next method, which is the Gaussian blur. So Gaussian basically does the same thing as averaging, except that instead of computing the average of all of the surrounding pixel intensity, each surrounding pixel is given a particular weight. And essentially the average of the products of those weights give you the value for the true center. Now using this method, you tend to get less blurring than compared to the averaging method, but the Gaussian blur is more natural as compared to averaging. So let's print that out. Let's call this Gauss and set this equal to cv.Gaussian blur, and this will take in the source image, so img, give it a kernel size of 7 by 7 just to compare it with the averaging. And another parameter that we need to specify is sigma x, or basically the standard deviation in the x direction, which for now we're just going to set as 0. And we can print that out, call this Gaussian blur, and pass in Gauss. Save that and run. If you compare it with this, you see that both of them use the same kernel size, but this is less blurred as compared to the averaging method. And the reason for this is because a certain weight value was added when computing the blur. Okay, so let's move on to the next method, and that is median blur. So let's go back to our image, and median blurring is basically the same thing as averaging, except that instead of finding the average of the surrounding pixels, it finds the median of the surrounding pixels. Generally, median blurring tends to be more effective in reducing noise in an image as compared to averaging and even Gaussian blur. And it's pretty good at removing some salt and pepper noise that may exist in the image. And generally, people tend to use this image in advanced computer vision projects that tend to depend on the reduction of substantial amount of noise. So let's go back here. And the way we apply the blur is by saying, let's call this median and set this equal to cv.median blur. We pass in the source image, and this kernel size will not be a tuple of 3 by 3, but instead just an integer, so 3. And the reason for this is because OpenCV automatically assumes that this kernel size will be a 3 by 3 just based off this integer. And we can print this out. Let's call this median blur and pass in median. And let's compare it with that. So let's set that to 7. And comparing it with Gaussian blur and averaging blur, you tend to look at this and you can make out some differences between the two images. So it's like as if this was your painting and it was still drying, and you take something and smudge over the image and you get something like this. Now generally median blurring is not meant for high kernel sizes like 7 or even 5 in some cases, and it's more effective in reducing some of the noise in the image. So let's change this all to 3 by 3. Let's copy that, change that to 3 by 3. And we can change that to 3. And now let's have a comparison between the three. This is your Gaussian blur, this is your averaging blur, this is your median blur. So compared with these two, you can see that there is kind of less blurring than Gaussian, but you can sort of make out the differences between the two. It's very subtle, but there are a couple of differences between the two. Finally, the last method we're going to discuss is bilateral blurring. Let's call this bilateral. Now, bilateral blurring is the most effective and sometimes used in a lot of advanced computer vision projects, essentially because of how it blurs. Now, traditional blurring methods basically blur the image without looking at whether you're reducing edges in the image or not. Bilateral blurring applies blurring but retains the edges in the image. So you have a blurred image, but you get to retain the edges as well. So let's call this bilateral and set this equal to cv.bilateral filter, and we pass in the image. We give it a diameter of the pixel neighborhood. Now notice this isn't a kernel size, but in fact a diameter. So let's set this to 5 for now. Give it a sigma color, which is basically the color sigma, the sigma color. A larger value for this color sigma means that there are more colors in the neighborhood that will be considered when the blur is computed. So let's set this to 15 for now. And sigma space is basically your space sigma. Larger values of this space sigma means that pixels further out from the central pixel will influence the blurring calculation. So let's set this to 15. So let's take a look at that sigma space thing. So for example, in bilateral filtering, if this is the value for this central pixel or the true center is being computed, by giving larger values for the sigma space, you essentially are indicating that whether you want pixels from this far away, or maybe this far away, or even this far away from influencing this particular calculation. So if you give like really huge numbers, then probably a pixel in this region might influence the computation of this pixel value. So let's set this to 15 for now, and let's display this image. So call the cv.imShow. Let's call this bilateral and pass in bilateral. Let's save that and run. And this is your bilateral image. So let's compare it with all the previous ones that we had. Compared with this, much better. Compared with averaging, way much better. Let's compare it with median. The edges are still there. It's slightly blurred. If you compare it with the original image, they kind of look the same thing. Okay, it kind of looks like there's no blur applied. So maybe let's increase this diameter to, I don't know, 10. And not much was done. The edges are still there. It kind of looks like the original image itself. So let's try and tune one of the other parameters. So let's set this to 35. Let's set this to 25. Yeah. We're really playing around with these values. And now you can basically make out now that this is starting to look a lot like median blur. When you give it large values, it's starting to show you that this is more looking like a smudged painting version of this image. Right, there's a lot of blur applied here, but the cats are looking smudged. So definitely keep that in mind when you are trying to apply blur in the image, especially with bilateral and median blurring, because higher values of the space sigma for bilateral or the kernel size for median blurring, and you tend to end up with a washed up, smudged version of this image. So definitely keep that in mind. But that kind of summarizes whatever we've done in this video. We discussed averaging, Gaussian, median, and bilateral blurring. So in the next video, we'll be talking about bitwise operators in OpenCV. So again, like always, if you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back to another video. In this video, we're going to be talking about bitwise operators in OpenCV. Now, there are four basic bitwise operators: AND, OR, XOR, and NOT. If you've ever taken an introductory CS course, you will probably find these terms familiar, bitwise operators. And they are in fact used a lot in image processing, especially when we're working with masks like we'll do in the next video. So at a very high level, bitwise operators operate in a binary manner. So a pixel is turned off if it has a value of 0 and is turned on if it has a value of 1. So let's actually go ahead and try to import numpy as np. And what I'm going to do is I'm going to create a blank variable and set this equal to np.zeros of size 400 by 400. And we can give it a data type of uint8. What I'm going to do is I'm going to use this blank variable as a basis to draw a rectangle and draw a circle. So I'm going to say rectangle is equal to cv.rectangle. We can say blank.copy. And we can pass in the starting point. So let's give it a margin of around 30 pixels on either side. So we're going to start from 30, 30, and we can go all the way across to 370, 370. And we can give it a color. Since this is not a color image, but rather binary image, we can just give it one parameter, so 255, white, and give it a thickness of -1 because we want to fill this image. And then I'm going to create another circle variable and set this equal to cv.circle. We're going to say blank.copy. We are going to give it a center, so the center will be the absolute center, so 200 by 200. And let's give it a radius of 200 and give it a color of 255. And let's fill in the circle, so -1. So let's display this image and see what we're working with. So call this rectangle and pass in the rectangle. And we're going to do the same thing with the circle. Let's call this circle and pass in the circle. Save that and run python bitwise.py. So we have two images that we're going to work with, this image of a rectangle and this image of a circle. So let's start off with the first basic bitwise operator, and that is bitwise AND. So before I actually discuss what bitwise AND really is, let me show you what it does. So essentially what I'm going to do is I'm going to say bitwise underscore AND is equal to cv.bitwise AND. And basically what I have to do is pass in two source images that are these two images, rectangle and circle. And we can display this image. Let's call this bitwise AND. Let's pass in bitwise AND. Save, run. And essentially you get back this image. So essentially what bitwise AND did was it took these two images, placed them on top of each other, and basically returned the intersection. Right? And you can make out, when you take this image, put it over this image, you have some triangles that are not common to both of these images, and so those are set to black or 0, while the common regions are returned. So the next one is basically bitwise OR. Now bitwise OR real simply returns both the intersecting as well as the non-intersecting regions. So let's try this. Bitwise OR is equal to cv.bitwise underscore OR. You pass in rectangle, we pass in circle, and we can print that. Let's call this bitwise OR and pass in bitwise. Oops, that was OR. Save that and run. And bitwise OR. Okay, this is bitwise OR. My mistake. Okay, so bitwise OR basically returned this funky looking shape. Essentially what it did is it took these two images, put them over each other, found the common regions, and also found the regions that are not common to both of these images, and basically superimposed them. So basically you can just put them together and find the resulting shape, and this is what you get. Put this image over this and you get this. Moving on. The next one is bitwise XOR, which basically is good for returning the non-intersecting regions. So this found the intersecting regions. This found the, let's get that back, the non-intersecting and intersecting regions, and XOR only finds the non-intersecting regions. So let's do that. Let's say bitwise, call this XOR is equal to cv.bitwise underscore XOR. We pass in the rectangle, and we pass in the circle. And we can display this. cv.imsure calls bitwise XOR, and we can pass in bitwise XOR. Save that and run. And here we have the non-intersecting regions of these two images when you put them over each other. Pretty cool. And just to recap, this bitwise AND again returns the intersecting regions. Bitwise OR returns the non-intersecting regions as well as the intersecting regions. Bitwise XOR returns the non-intersecting regions. So essentially, if you take this bitwise XOR and subtract it from bitwise OR, you get bitwise AND. And conversely, if you subtract bitwise AND from bitwise OR, you get bitwise XOR. So essentially, that's a good way of visualizing what exactly happens with these bitwise operators. And finally, the last method we can discuss is bitwise NOT. Essentially, it doesn't return anything. What it does is it inverts the binary color. So let's do that. So let's call this bitwise NOT is equal to cv.bitwise underscore NOT. And this only takes in one source image. So let's set this to the rectangle for now. And we can display this. Let's call this rectangle NOT. And we can pass in bitwise NOT. Save that and run. Basically what it did is, if you look at this image, it found all the white regions, all the white pixels in the image, and inverted them to black. And all the black images, it inverted to white. Essentially, it converted the white to black and from black to white. So we can try that with this circle. Let's call this circle. We can pass in the circle here. Save and run. And the resultant circle knot that you get is this. This is a white hole, this is a black hole for physicists out there. Okay, so that's pretty much it for this video. I just wanted to introduce you all to the idea of bitwise operations and how it works. In the next video, we'll be actually talking about how to use these bitwise operations in a concept called masking. So if you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back. In this video, we're going to be talking about masking in OpenCV. Now, in the previous video, we discussed bitwise operations. And using those bitwise operations, we can essentially perform masking in OpenCV. Masking essentially allows us to focus on certain parts of an image that we'd like to focus on. So, for example, if you have an image of people in it, and if you're interested in focusing on the faces of those people, you could essentially apply masking and essentially mask over the people's faces and remove all the unwanted parts of the image. So that's basically a high-level intuition behind this. So let's actually see how this works in OpenCV. So I've basically read in a file and I've displayed that image. The other thing I want to do is I want to import numpy as np. What I'm going to do is I'm going to say blank is equal to np.zeros of size image dot shape of the first two values. Now this is extremely important. The dimensions of the mask have to be the same size as that of the image. If it isn't, it's not going to work. And we can give it a data type of uint8. UINT 8. If you want to display this, we can display this. It's just going to be a blank image. So let's call this blank image and pass in blank. Essentially what I'm going to do is I'm going to draw a circle over this blank image and call that my mask. So I'm going to say mask is equal to cv.circle. We're going to draw on the blank image. On the blank image, we can give it a center of this image. So let's say image.shape of 1 divided by 2, and image.shape of 2, image.shape of 0 divided by 2. And we can give it a radius of, I don't know, let's say 100 pixels. Give it a color of 255. Give it a thickness of -1. And we can visualize our mask as mask and pass in mask. So let's run that. Python masking.py. And this is essentially our mask. This is the blank image we're working with, and this is the image that we want to mask over. So let's actually create a masked image. We're going to say masked image is equal to cv.bitwise_end, the source image, so img, and we specify the parameter mask is equal to mask, which is this circle image over here. And we can display this image, call this masked image, and we can pass in masked. Save that and run. And this is essentially your masked image. You took this image, you put this image over it, and found the intersecting region. Okay, by optionally passing the mask is equal to mask. That's exactly what we're doing. Cool. So let's try and play around with this. Let's maybe move this by, I don't know, a couple of pixels around. So let's say 45. Save and run. It moves down, right? So to shape of 0. Okay, this has to be 45 plus 45. Save that and run. And we get the image of the cat. We can draw a circle. We can draw a rectangle instead. Let's pass on blank. Let's give it that. Let's give it that and give it a starting endpoint of, let's copy this and add a couple of pixels. So maybe 100 pixels this way and 100 pixels this way. We can get rid of this, we don't need that, save that and run. This is the square, and this is essentially the masked image. So let's actually try this with a different image. So over here I've got an image. Let's try it with maybe these cats 2. Let's go back to cats 2. Save that. Run. And this is the mask that we get by putting these two over each other. And essentially you can play around with these as you feel fit. You can maybe try different shapes, weird shapes. And the way you can get these weird shapes is essentially creating a circle, a rectangle, and applying bitwise and you get this weird shape. And then you can use that weird shape as your mask. So let's just try that. Let's try that. We're gonna say let's call this circle and blank.copy. Copy and create a rectangle. Let's just grab it from this where were we? From bitwise. Let's grab this. Let's grab rectangle. Copy that. Paste that there. Blank.copy 3030. Okay, blank the same shape. Okay, let's create this weird shape. Is equal to cv.bitwise_end of this circle, this rectangle, and we don't need to specify anything else. Let's try to visualize this. Let's close this out. Try to cv.onShow, call this the weird shape. pass in the weird shape. Say run. Mask is not defined. Where's mask? Where's mask? Okay, find that out. Okay, this is the weird shape that we get. We're not really going for a half moon, but hey, whatever. Let's close this out. Use this weird shape as a mask. So use weird shape as a mask, and let's see the final masked image. And this is essentially your weird shape masked image. Let's call this a weird shape masked image. Weird shaped masked image. This little half moon here. And essentially you can do pretty much anything you want with this. You can experiment with various shapes and sizes and stuff like that. But just know that the size of your mask has to be of the same dimensions as that of your image. If you want to see why, let's maybe subtract 100 pixels. Not possible, but unsupported, yeah. Though that's maybe like subtract tuple 100. Don't know whether that'll work, but it doesn't work. Okay, so let's just say image.shape of 1. Okay, let's just give it a different size. Why are we even using image? Let's give it a size of 300 by 300. Definitely not the size of this. And we get this. Assertion failed, mtype blah 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 mask.same size in function whatever. So essentially these need to be of the same size, otherwise it's going to fail and throw you an error. So that's it for this video. We talked about masking. Again, nothing too different. We've essentially used the concept of bitwise AND from the previous video. And you'll see that when we move on to computing histograms in the next video, where masking really comes into play and how masking really affects your histograms. So if you have any questions, again, leave them in the comments below. Otherwise, I'll see you in the next video. Hey everyone, and welcome back to another video. In this video, we're going to be talking about computing histograms in OpenCV. Now, histograms basically allow you to visualize the distribution of pixel intensities in an image. So whether it's a color image or whether it's a grayscale image, you can visualize these pixel intensity distributions with the help of a histogram, which is kind of like a graph or a plot that will give you a high-level intuition of the pixel distribution in the image. So we can compute a histogram for grayscale images and compute a histogram for RGB images. So we're going to start off with computing histograms for grayscale images. And so let's just convert this image to grayscale by saying cvt.cvt color. Let's pass the image and give it a color code of color underscore BGR to gray. And we can display this image. Let's call this gray and pass it gray. Now, to actually compute the grayscale histogram, what we need to do is essentially call this gray underscore hist and set this equal to cv.calc hist. This method will essentially compute the histogram for the image that we pass into. Now this images is a list, so we need to pass in a list of images. Now since we're only interested in computing a histogram for one image, let's just pass in the grayscale image. The next thing we have to pass in is the number of channels, which basically specify the index of the channel we want to compute a histogram for. Now since we are computing a histogram for a grayscale image, let's wrap this as a list and pass in 0. The next thing we have to do is provide a mask. Do we want to compute a histogram for a specific portion of an image? We will get to this later, but for now, just set this to none. A hist size is basically the number of bins that we want to use for computing the histogram. Essentially, when we plot a histogram, I'll talk about this concept of bins. But essentially, for now, just set this to 256, wrapped as a list. So let's wrap that as a list. And the next thing I want to do is specify the range of all possible pixel values. Now for our case, this will be 0 to 256. And that's it. So to plot this image, let's actually use matplotlib. So import matplotlib.pyplot as plt, and then we can instantiate a plt.figure, a plt figure. Let's give it a title. Let's call this grayscale histogram. We can essentially give it a label across the x-axis, and we're going to call this bins. Let's give this a y label and set this equal to the number of pixels, and that's y label. And finally, we can plot by saying plt.plot the grayscale histogram. And finally, we can essentially give it a limit across the x-axis, so plt.xlim of a list of 0 to 256. And finally, we can display this image, so plt.show. Save that and run python histogram.py. And this is the distribution of pixels in this image. As you can see, the number of bins across the x-axis basically represent the intervals of pixel intensities. So as you can see that there is a peak at this region. This means that this is closely at 50, 60-ish. So this means that in this image, there are close to 4,000 pixels that have an intensity of 60. And as you can see that there's a lot of peaking in this region. So between probably 40 to 70, there's a peak of pixel intensities of close to 4,000 pixel intensities in this image. So let's try this with a different image. Let's try this with the cats _2. Save that and run. And there is a peaking of pixel values in between 200 and 225. And this makes sense because most of the image is white. So given that reason, we can probably deduce that there will be a peaking towards white, or 255. So this is essentially computing the grayscale histogram for the entire image. What we can do is we can essentially create a mask and then compute the histogram only on that particular mask. So let's do that. Let's go back to masking. Let's grab this. Let's grab this. Let's go right up there. I set this to image.shape of the first two values. The sizes are the same. Let's essentially draw a mask, which will be cv.circle of blank, and we can give it a center of image.shape of 1 divided by 2, and image.shape of 0 divided by 2. Give it a radius of 100 pixels, give it a color of 255, give it a thickness of -1. We can display a mask. Let's call this mask, pass in mask. And here's where things get interesting. We compute the grayscale histogram for this mask. And the way we do that is by setting this mask parameter to mask. So instead of none, we set this to mask. And let's see what that does to our histogram. NP is not defined. Great. Save that and run. And I kind of made a mistake here. That's right. This is the mask. This is not exactly the mask. This is a circle. This is this will be a circle. And essentially we need to mask out the image. So the way we do that is by creating a mask and setting this equal to cv.bitwise underscore, and we can pass in the grayscale image, and we can pass in the mask, which is equal to circle. And now we can use that as the mask. So we didn't display that, so X. Yeah. Sorry, I made a mistake, but hopefully things should be fine right now. So this is the mask, and this is the histogram computed for this particular mask. As you can see that there is a peaking of pixel intensity values in this region, and there are smaller peakings in these regions down below. Let's try this with another image. Let's pass in the cats.jpg. This is our mask, and this is the there is a peaking in this image towards 50. Okay, so that was it for computing grayscale histograms. Let's move on to try to compute a color histogram. That is to compute a histogram for a color image, so an RGB image. So let's call this color histogram. And the way we do that is, instead of converting this image to grayscale, let's comment all of this out. We'll use a mask, but later. Let's comment all of this out. This mask will be for IMG, and yeah, that's pretty much it. So let's start with the color histogram. The way we do that is, let's define a tuple of colors and set this equal to B, then tuple of G, a tuple element of R. And what I'm going to do next is I'm going to say for I, call in enumerate of colors. What I'm going to do is I'm going to say hist. So I'm going to plot the histogram by saying cv.calc hist. We're going to compute it over the image itself. The channels will be I. That means this I over here. We're going to provide a mask of none for now. Give it a hist size of 256 and give it a ranges of 0 to 256. And then let's do a plt.plot a hist and give it a color equal to col. And finally we can do a plt.xlim of 0 to 256. And for this purpose we can essentially grab this, copy that, uncomment this out, and we can do a plt.show. So this should work. I'm missing something out. I don't think I am. We're not computing this histogram for a mask, or we'll do that next. But let's save that and run. Ah, cool. And let's close that out. I made a mistake. This is a color histogram. Shouldn't make much of a difference, but hey. So this is the color histogram that we get for the original image, not for a mask, but in fact this image. So as you can see, that this color image basically computed the plot for the blue channel, the red channel, and the green channel as well. So using this, you can basically make out that there is a peaking of blue pixels that have a pixel intensities of 30. There's a peaking of red at probably around 50. Peaking of green, probably around 80, 75 to 80. Cool, and using this you can basically make out the distribution of pixel intensities of all three color channels. So let's try and apply a mask by setting this equal to mask. Let's see whether we have everything in order. This is a bit wide and mask, save that and run. Mask are not the same size. Okay, I finally got the error. So basically the mask needs to be a binary format. So instead of passing in this mask, this will actually be the masked image. We can pass this, make that mask, and we can change the circle to mask. Now this should work without any errors. And we can change that to masked. And let's run that. And now we get the color histogram for this particular mask. I made a mistake because I used this as my mask to compute the histogram for one channel. The problem was this masked image was actually of 3 channels, and I attempted to use these 3-channeled mask to calculate the histogram per channel, which isn't allowed in OpenCV. So that was my mistake. I kind of used the wrong variable names, so got confused. But essentially this is it. You're computing the histogram for a particular section of this image, and this is what you get. There is a high peaking of red in this area, high peaking of blue in this area, and high peaking of green somewhere over here. So essentially that's it for this video. Histograms actually allow you to analyze the distribution of pixel intensities, whether for a grayscale image or for a colored image. Now these are really helpful in a lot of advanced computer vision projects when you're actually trying to analyze the image that you get and maybe try to equalize the image so that there's no peaking of pixel values here and there. In the next video we'll be talking about how to threshold an image and the different types of thresholding. As always, if you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next video. Hey everyone, and welcome back to another video. In this video, we're going to be talking about thresholding in OpenCV. Now, thresholding is the binarization of an image. In general, we want to take an image and convert it to a binary image. That is, an image where pixels are either 0 or black, or 255 or white. Now, a very simple example of thresholding would be to take an image and take some particular value that we're going to call the thresholding value and compare each pixel of the image to this thresholded value. If that pixel intensity is less than this threshold value, we set that pixel intensity to 0, and if it is above this thresholded value, we set it to 255 or white. So in this sense, we can essentially create a binary image just from a regular standalone image. So in this video, we're actually going to talk about two different types of thresholding: simple thresholding and adaptive thresholding. So let's start off with simple thresholding. So in essence, what I want to do is, before I talk about simple thresholding, is I want to convert this BGR image to grayscale. So I'm going to say gray is equal to cv.cvt color. We pass in the image, we pass in the color code, which is BGR to gray. We can display this image, call this gray, we can pass in gray. Cool. So let's start off with the simple thresholding. So essentially to apply this idea of simple thresholding, we essentially use the cv.threshold function. Now this function returns threshold and thresh, which is equal to cv.threshold. And this in essence takes in the grayscale image. The grayscale image has to be passed in to this thresholding function. Then what we do is we pass in a thresholded value. So let's set this to 150 for now. And we have to specify something called a maximum value. So if that pixel value is greater than 150, what do you want to set it to? In this case, we want to binarize the image, so we set it to 255. And finally, we can specify a thresholding type. Now this thresholding type is essentially cv.thresh_binary. And what this does is it basically looks at the image, compares each pixel value to this thresholded value, and if it is above this value, it sets it to 255. Otherwise, it infers that if it falls below, it sets it to 0. So essentially, it returns two things: thresh, which is the thresholded image or the binarized image, and threshold, which is essentially the same value that you passed, 150. The same thresholded value you pass in will be returned to this thresholded value. So let's actually display this image. So let's say cv.imShow, we'll call this thresholded. We'll call this simple thresholded, and we can pass in thresh. So let's save that and run python thresh.py. And this is a thresholded image that you get. Again, this is nothing too different from when we discussed thresholding in one of the previous videos, but this is essentially what you get. So let's play around with these threshold values. Let's set this to 100 and let's see what that does. And as a result, more parts of the image have become white. So And of course, if you give it a higher value, less parts of the image will be white. So let's set this to 225. And very few pixels in this thresholded image actually have a pixel intensity of greater than 225. So what we can do after this is essentially create an inverse thresholded image. So what we could do is we could essentially copy this, and instead of saying thresh, I'm going to say thresh underscore inverse, and I'm going to leave everything else the same. Let's set this to 150, and the same thing here. And instead of passing in the type of thresholding, I'm going to say cv.thresh underscore binary underscore inverse. And let's call this thresholded inverse, and we can pass in inverse. So let's save that and run. And this is essentially the inverse of this image. Instead of setting pixel intensities that are greater than 150 to 255, it sets whatever values that are less than 150 to 255. So that's essentially what you get, right? All the black parts of this image would change to white, and all the white parts of the image would change to black. Cool, so that's it for simple thresholding. Let's move on now to adaptive thresholding. Adaptive thresholding. Now, as you can imagine, we got different images when we provided different thresholded values. Now, kind of one of the downsides to this is that we have to manually specify a specific thresholded value. Now, some cases this might work, in more advanced cases this will not work. So one of the things we could do is we could essentially let the computer find the optimal thresholded value by itself. And using that value that it finds, it binarizes over the image. So that's in essence the entire crux of adaptive thresholding. So let's set up a variable called adaptive underscore thresh and set this equal to cv.adaptive threshold, and inside I want to pass in a source image. So let's set this to gray. I want to pass in a maximum value, which is 255. Now notice there is no thresholded value. Adaptive method basically tells the machine which method to use when computing the optimal threshold value. So for now we're just going to set this to the mean of some neighborhood of pixels. So let's set this to cv.adaptive underscore thresh underscore mean underscore c. Next, we'll set up a threshold type. This is cv.thresh underscore binary. Again, nothing too different from this from the first example. And two other parameters that I want to specify is the block size, which is essentially the neighborhood size or the kernel size, which OpenCV needs to use to essentially compute the mean to find the optimal threshold value. So for now, let's set this to 11. And finally, the last method we have to specify is the C value. Now this C value is essentially an integer that is subtracted from the mean, allowing us to essentially fine-tune our thresholding. So again, don't worry too much about this. You can set this to 0, but for now, let's set this to 3. And finally, once that's done, we can go ahead and try to display this image. So let's call this adaptive thresholding, and we can pass in adaptive thresh. So let's save that and run. And this is essentially your adaptive thresholding method. So essentially what we've done is we've defined a kernel size or window that is drawn over this image. In our case, this is 11 by 11. And so what OpenCV does is it essentially computes a mean over those neighborhood of pixels and finds the optimal threshold value for that specific part. And then it slides over to the right, and it slides and does the same thing, and it slides down and does the same thing, so that it essentially slides over every part of the image. So that's how adaptive thresholding works. If you wanted to fine-tune this, we could change this to a thresh underscore binary underscore inverse, just to see what's really going on under the hood. Cool, so all the white parts of the image will change to black, and all the black parts of the image will change to white. So let's play around with these values. Let's set this to probably 13 and see what that does. Okay, definitely some difference from the previous hyperparameter. So let's set this to 11 and let's set this to maybe 1. Okay, definitely more white. Let's set this to maybe 5. And really, you can play around with these values, right? The more you subtract from the mean, the more accurate it is, right? You can basically make out the edges now in this basket. So let's maybe increase that to 9. And you get less white parts in the image, but essentially now you can make out the features better. Cool. So that was essentially adaptive thresholding. Adaptive thresholding that essentially computed the optimal threshold value on the basis of the mean. Now we don't have to stick with the mean. We can go with something else. So instead of mean, let's set this to Gaussian. So let's save that and see what that does. And this is the thresholded image using the Gaussian method. So the only difference that Gaussian applied was essentially add a weight to each pixel value and computed the mean across those pixels. So that's why we were able to get a better image than when we used the mean. But essentially the adaptive thresholding mean works in some cases, the Gaussian works in other cases. There's no real one size fits all. So really play around with these values, see what you get. But that's essentially all we have to discuss for this video. We talked about 2 different types of thresholding, simple thresholding and adaptive thresholding. In simple thresholding, we have to manually specify a threshold value, and in adaptive thresholding, OpenCV does that for us using a specific block size or a kernel size, and either computing the thresholded value on the basis of the mean or on the basis of the Gaussian distribution. So in the next video, the last video in the advanced section of this course, we're going to be discussing how to compute gradients and edges in an image. So if you have any questions, leave them in the comments below. I'll be sure to check them out. Otherwise, I'll see you guys in the next video. Thanks for watching. Hey everyone, and welcome back to another video. In this video, we're going to be talking about gradients and edge detection in OpenCV. Now you can think of gradients as these edge-like regions that are present in an image. Now they're not the same thing. Gradients and edges are completely different things from a mathematical point of view. But you can pretty much get away with thinking of gradients as edges from a programming perspective only. So essentially, in the previous videos, we've discussed the canny edge detector, which is essentially kind of an advanced edge detection algorithm that is essentially a multi-step process. But in this video, we're going to be talking about 2 other ways to compute edges in an image. And that is the Laplacian and the Sorbel method. So let's start off with the Laplacian. So the first thing I want to do is I want to convert this image to grayscale by calling the CVT to a color method. We pass in the image and we say cv.color_bgr to gray. We can display this image. Let's call this gray, and we can pass in gray. So let's start off with the Laplacian. So we're going to define a variable called lap and set this equal to cv.Laplacian. And what this essentially will do is it will take in a source image, which is gray for now, and it will take in something called a D depth or data depth. Now for now, we'll set this to cv.64f. And just follow along with whatever I do next. I'm going to say lap is equal to np.uint8. And instead, I'm going to pass in np.absolute, and we can pass in lap. And since I'm using NumPy, I can actually go ahead and import NumPy as np. And when I go to display this image, calling the cv.imShow method, let's call this Laplacian, and we can pass in lap. Call a lap, save, and run. And call this Python gradients.py. Invalid syntax, okay, it's cv.cv_64f. Say that. And this is essentially the Laplacian edges in the image. Kind of looks like an image that is drawn over a chalkboard and then smudged just a bit. But anyway, this is the Laplacian method. Let's try this with another image. Let's try this with this park call this Boston. Let's call this the park. Save that and run. And this essentially looks like a pencil shading of this image. So all the edges that exist in the image, or at least most of the edges in the image, are essentially drawn over with a pencil and then lightly smudged. So that's essentially the Laplacian edges, you could say. So again, don't worry too much about why we converted this to an UINT and then we computed the absolute value. But essentially the Laplacian method computes the gradients of this image, the grayscale image. Generally this involves a lot of mathematics, but essentially when you transition from black to white and white to black, that's considered a positive and a negative slope. Now, images itself cannot have negative pixel values. So what we do is we essentially compute the absolute value of that image. So all the pixel values of the image are converted to their absolute values, and then we convert that to a UINT8. So an image-specific data type. So that's basically the crux of what's going on right over here. So let's move on to the next one, and that is the Sobel gradient magnitude representation. So essentially the way this does is that Sobel computes the gradients in two directions, the x and the y. So we're going to say Sobel x, which is the gradients that are computed along the x-axis, and set this equal to cv.sobel, and we can pass in the image. So let's set this to the grayscale image. We pass in a data depth, which is cv.cv_64f, and we can give it an x direction, so let's set this to 1, and the y direction we can set that to 0. And let's copy this and call it Sobel y, and instead of 1, 0, we can say 0, 1. And we can visualize this. Let's print, let's call this Sobel x, and we can pass in Sobel x, and we can say cv.show Sobel y, and set this to Sobel y. Call that. And these are essentially the gradients that are computed. This is over the y-axis, so you can see a lot of y horizontal specific gradients, and the Sobel x was computed across the y-axis, so you can see y-axis specific gradients. Now we can essentially get the combined Sobel image by essentially combining these two, the Sobel x and the Sobel y. And the way we do that is we're going to say combined underscore Sobel, and set this equal to cv.bitwise underscore or, and we can pass in Sobel x and Sobel y. And we can display this image, so let's call cv.imshow. We could say combined Sobel, and we could pass in the combined Sobel. So let's run that. And this is essentially the combined Sobel that you get. Let's go back here. So it essentially took these two, applied cv.bitwise or, and essentially got this image. So if you want to compare this with the Laplacian, two completely different algorithms, so the results you get will be completely different. Okay, so let's compare both of these, Laplacian and the Sobel, with the Kenny edge detector. So let's go down here. Let's say Kenny is equal to cv.kenny, and we can pass in the image. So let's pass in the grayscale image. Let's give it two threshold values of 150 and 175, and we're done. Let's display this image. Let's call this Kenny. We can pass in Kenny. So let's save that and let's see what that gives us. So let's compare that with here, here, and here. So that's essentially it. This is the Laplacian gradient representation, which essentially returns kind of this pencil shading version of the image, of the edges in the image. Combined Sobel computes the gradients in the x and the y direction, and we can combine these two with bitwise OR. And Kenny is basically a more advanced algorithm that actually uses Sobel in one of its stages. Like I mentioned, Kenny is a multi-stage process, And one of its stages is using the Sobel method to compute the gradients of the image. So essentially, you see that the Kenny edge detector is a more cleaner version of the edges that can be found in the image. So that's why in most cases you're going to see the Kenny used, but in more advanced cases you're probably going to see a Sobel used a lot. Not necessarily Laplacian, but Sobel definitely. So that's pretty much it for this video, and in fact this video concludes the advanced section of this course. Moving on to the next section, we will be discussing face detection and face recognition in OpenCV. We're actually going to touch on using Haar cascades to perform some face detection, and in face recognition we actually have two parts. Face recognition with OpenCV's built-in face recognizer, and in the second part we'll be actually building our own deep learning model to essentially recognize some faces in an image. Again, like always, if you have any questions, leave them in the comments below. Otherwise, I'll see you guys in the next section. Hey everyone, and welcome back to another video. We are now at the last part of this Python and OpenCV course, where we are going to talk about face detection and face recognition in OpenCV. So what we're going to be doing in this video is actually discussing how to detect faces in OpenCV using something called a Haar cascade. In the next video, we will talk about how to recognize faces using OpenCV's built-in face recognizer. And after that, we will be implementing our own deep learning model to recognize between the Simpson characters. We're going to create that from scratch and use OpenCV for all the pre-processing and displaying of images and stuff like that. So let's get into this video. Now, face detection is different from face recognition. Face detection merely detects the presence of a face in an image, while face recognition involves identifying whose face it is. Now, we'll talk more about this later on in this course, but essentially face detection is performed using classifiers. A classifier is essentially an algorithm that decides whether a given image is positive or negative, whether a face is present or not. Now, a classifier needs to be trained on thousands and tens of thousands of images with and without faces, but fortunately for us, OpenCV already comes with a lot of pre-trained classifiers that we can use in any program. So essentially, the two main classifiers that exist today are Haar cascades and more advanced classifiers called local binary patterns. We're not going to talk about local binary patterns at all in this course, but essentially they're more advanced Haar cascade classifiers. They're not as prone to noise in an image as compared to the Haar cascades. So I'm currently at the OpenCV's GitHub page where they store their Haar cascades, their Haar cascade classifiers. And as you can see, there are plenty of Haar cascades that OpenCV makes available to the general public. You have a Haar cascade for an eye, a frontal cat face, a frontal face default, full body, your left eye, a Russian license plate, a Russian plate number, I think that's the same thing, a Haar cascade to detect a smile, a Haar cascade for detection of the upper body, and things like that. So feel free to use whatever you want, but in this video we're going to be performing face detection, and for this we're going to use the Haar cascade underscore frontal face underscore default.xml. So when you go ahead and open that, you're going to get about 33,000 lines of XML code. So all of this. So what you have to do is essentially go to this raw button and you'll get all this raw XML code. All you have to do is click Ctrl A or Command A if you're on a Mac, and click Ctrl C or Command C, and then go to your VS Code or your editor and create a new file, and we're going to call this har underscore face.xml. And inside this, I want to paste in those 33,000 lines of XML code. Go ahead and save that, and our classifier is ready. So we can go ahead and close this out. So we're going to be using this Haar cascade classifier to essentially detect faces that are present in an image. So in this file called face_detect.py, I've imported OpenCV. I've basically read in an image of a lady, a person. That is this image over here. And we can go real quick and display this. So let's run python face_detect.py. And we get an image in a new window. Cool. So let's actually implement our code. The first thing I want to do is convert this image to grayscale. Now, face detection does not involve skin tone or the colors that are present in an image. These HER cascades essentially look at an object in an image and using the edges tries to determine whether it's a face or not. So we really don't need color in our image, and we can go ahead and convert that to grayscale. cv.cvt color, pass in the image, and cv.color_bgr to gray. And we can display this. Let's call this gray. Let's call this gray person. And we can pass in the img. Let's save that and run. And we have to pass in the gray. Okay, we have a gray person over here. So let's move on to essentially reading in this har_face.xml file. So the way we do that is by essentially create a har cascade variable. So let's set this to har_cascade. And we're going to set this equal to cv.cascade classifier. And inside, what I essentially want to do is pass in the path to this XML file. So that is as simple as saying har_face.xml. So this cascade classifier class will essentially read in those 33,000 lines of XML code and store that in a variable called har_cascade. So now that we've read in our har cascade file, let's actually try to detect the face in this image over here. So what I'm going to do is essentially say faces_rect is equal to har_cascade dot detect multiscale, and inside we're going to pass in the image that we want to detect face on. So this is gray. We're going to pass in a scale factor. For now, let's set this to 1.1. Give it a variable called minimum neighbors, which essentially is a parameter that specifies the number of neighbors a rectangle should have to be called a face. So let's set this to 3 for now. So that's it. That's all we have to do. And essentially what this does is this detect multiscale, an instance of the cascade classifier class, will essentially take in this image, use these variables called scale factor and minimum neighbors to essentially detect a face and return essentially the rectangular coordinates of that face as a list to faces_rect. That's exactly why we are giving it faces_rect. It's a rectangle. So you can essentially print the number of faces that were found in this image by essentially printing the length of this faces_rect variable. So let's do that. Let's print, say, number of faces found is equal to, we can pass in the length of faces_rect. So let's save that and run. And as you can see that the number of faces that were found were 1. And that's true because there's only one person in this image. Cool. Now, utilizing the fact that this faces_rect is essentially the rectangular coordinates for the faces that are present in the image, what we can do is we can essentially loop over this list and essentially grab the coordinates of those images and draw a rectangle over the detected faces. So let's do that. So the way we do that is by saying for x, y, w, h in faces_rect. What we're going to do is we're going to draw a rectangle, cv.rectangle, over the original image, so img, give it a point 1. This point 1 is essentially x, y, and point 2 is essentially x plus w, y plus h. Let's give it a color. Let's set this to green, so 0, 255, 0. Give it a thickness of 2. And that's it, and we can print this, and we can display this image. So let's set this to detected faces. And we can pass in OMG. And if you look at this image, you can essentially see the rectangle that was drawn over this image. So this in essence is the face that OpenCV's hard cascades found in this image. So let's try this with another image. So what I have here are a couple of other people, an image of 5 people. So we're going to use that image and try to see how many faces OpenCV's hard cascades could detect in this image. So let's set this to group 2, and we can change that to group of 5 people. Save that, call it great people. Save and run. And I want to point real quick that the number of faces that were found were actually 7. Now we know that there are 5 people in this image, so let's actually see what OpenCV thought was a face. So we can go real quick. So actually it detected all the faces in this image, all the 5 people, but it also detected 2 other, I guess a stomach and part of a neck. Now this is to be expected because hard cascades are really sensitive to noise in an image. So if you have something that pretty much looks like a face, like her neck looks like a face, it has the same structure as a typical face would have. I don't know why her stomach was recognized as a face, but again, this is to be expected. So one way we can try to minimize the sensitivity to noise is essentially modifying the scale factor and minimum neighbors. So let's increase the minimum neighbors to maybe 6 or 7. Save that and run. And as you can see, now 6 faces were found. So I guess by increasing the minimum neighbors parameter, we essentially stopped OpenCV from detecting her stomach as a face. So let's try this with another more complex image. A couple of people in group 1. So let's change that to group 1, save, run. Now as you can see that the number of faces that were found was 6, and we know that this is not 6. So let's actually change this minimum neighbors just a bit. Let's change this first to 3 and see how many faces were found. Now we got 14. Okay, some people at the back weren't chosen because either the faces are not perfectly perpendicular to the camera, or they're wearing some accessories on their face. For example, eyeglasses, this dude's wearing a hat, this dude's wearing a cap, and stuff like that. So let's actually change this to 1, and let's see where that gets us. Change that to 1, save, run. And now we got 19 faces that were found in this image. So essentially by looping through these values, by changing these values, by tweaking these values, you can essentially get a more robust result. But of course, by minimizing these values, you're essentially making OpenCV's hard cascades more prone to noise. So that's a trade-off you need to consider. Now again, hard cascades are not the most effective in detecting faces. They're popular, but they're not the most advanced. They're probably not what you would use if you were to build more advanced computer vision projects. I think for that, dlib's face recognizer is more effective and less sensitive to noise than OpenCV's hard cascades. It's as per your use case. Hard cascades are more popular, they're easy to use, and they require minimal setup. And if you wanted to extend this to videos, you could. All you have to do is essentially detect hard cascades on each individual frame of a video. Now, I'm skipping that because it's pretty self-explanatory. So that's pretty much it for this video. We discussed how to detect faces in OpenCV using OpenCV's hard cascades. In the next video, we will actually talk about how to recognize faces in OpenCV using OpenCV's built-in face recognizer. So, like always, if you have any questions, comments, concerns, whatever, leave them in the comments below. Otherwise, I'll see you in the next video. Hey everyone, and welcome back to another video. In this video, we will learn how to build a face recognition model in OpenCV using OpenCV's built-in face recognizer. Now, in the previous video, we dealt with detecting faces in OpenCV using HAR cascades. This video will actually cover how to recognize faces in an image. So what I have here are 5 folders of 5 different people. Inside each folder, I have about 20 images of that particular person. So Jerry has 21 images, Elton has 17, Mindy Kaling has 22, Ben Affleck has 14, and so on. So what I'm essentially going to do is we're going to use OpenCV's built-in face recognizer, and we're going to train that recognizer on all of these images in these 5 folders. Now this is sort of like building a mini-sized deep learning model, except that we're not going to build any model from scratch. We're going to use OpenCV's built-in face recognizer. All we're going to do is we're actually going to pass in these close to 90 images, and we're going to train that recognizer on these 90 images. So let's create a new file, and we're going to call this faces_train.py. We're going to import OS, we're going to import CV2 as CV, and we're going to import NumPy as NP. So the first thing I want to do is essentially create a list of all the people in the image. So this is essentially the names of the folders of these particular people. What you could do is you could manually type those in, or you could essentially create an empty list. Let's call this P, and we can loop over every folder in this folder. Let's set this to an R string, and we can say p.append I, and we can print p. Let's save that and run python faces_train.py, and we get the same list that we got over here. So that's one way of doing it. And what I'm going to do next is I'm essentially going to create a variable called dir and set this equal to this base folder. That is this folder which contains these 5 folders of these people. Cool. So with that done, what we can do is we can essentially create a function called def create_train that will essentially loop over every folder in this base folder, and inside that folder it's going to loop over every image and essentially grab the face in that image and essentially add that to our training set. So our training set will consist of 2 lists. The first one is called features, which are essentially the image arrays of faces. So let's set this to an empty list. And the second list will be our corresponding labels. So for every face in this features list, what is its corresponding label, or whose face does it belong to? Like one image could belong to Ben Affleck, the second image could belong to Elton John, and so on. So let's create a function. So we're going to loop over every person in this people list. We're going to grab the path for this person. So for every folder in this base folder, going through each folder and grabbing the path to that folder. So that's essentially as simple as saying os.path.join, and we can join the dir with person. And what I'm going to do is I'm going to create a label variable and set this equal to people.index of person. And now that we're inside each folder, we are going to loop over every image in that folder. So we're going to say for image in os.list_dir in path, we are going to grab the image path. So we're going to say image_path is equal to os.path.join. We're going to say join. We're going to join the path variable to the image. Now that we have the path to an image, we're going to read in that image from this path. So we're going to create a variable called img_array is equal to cv.imread image underscore path. We're going to convert this image to grayscale by saying cvt color, pass in img underscore array, and we can pass in cv.color underscore bgr to gray. Cool, and now with that done, we can essentially try to detect the faces in this image. So let's go back to face underscore detect and grab the har cascade classifier variable here. Let's paste that there. And we can create our faces underscore rect and set this equal to har underscore cascade dot detect multi-scale. This will take in the gray image, the scale factor of 1.1 and a minimum neighbors of 4. And we can loop over every face in this faces rect. So for x, y, w, each in faces rect, we are going to grab the faces region of interest and set this equal to, and basically crop out the face in the image. So we're going to say gray, y to y plus h, and x to x plus w. And now that we have a face region of interest, we can append that to the features list, and we can append the corresponding label to the labels list. So we're going to do features dot append. We're going to pass in faces underscore ROI, and we can do a labels dot append label. This label variable is essentially the index of this list. Now, the idea behind converting a label to numerical values is essentially reducing the strain that your computer will have by creating some sort of mapping between a string and the numerical label. Now, the mapping that we are going to do is essentially the index of that particular list. So let's say that I grab the first image, which is an image of Ben Affleck. The label for that would be 0, because Ben Affleck is at the 0th index of this people list. Similarly, Elton John, an image of Elton John would have a label of 1 because it is at the 2nd position or the 1st index in this people's list. So that's essentially the idea behind this. Now, with that done, we can essentially try to run this and see whether we got any errors or not. And we can print the length of the features. So let's say length of the features list is equal to the length of features, and we can do the same thing. Let's copy this. Length of the labels list, set this to length of labels. So that shouldn't give us any error. So let's run that. And we get the length of the features 100 and length of the labels 100. So essentially what we have are 100 faces and 100 corresponding labels to those faces. So we don't need this anymore. What we can do is we can essentially use this features and labels list, now that it's appended, to train our recognizer on it. So the way we do that is we instantiate our face recognizer, call this as an instance of the cv.face.lbph face recognizer underscore create class. And this will essentially instantiate the face recognizer. Now we can actually train the recognizer on the features list and the labels list. So the way we do that is by saying face underscore recognizer dot train, and we can pass in the features list and we can pass in the labels list. And before I actually do that, I do want to convert this features and labels list to NumPy arrays. So we're going to say features is equal to np.array of features, and we can say labels is equal to np.array of labels, and save that and run. Okay, dtype object. So let's set this to dtyped object. Pass in dtype is equal to object. And we can actually print when this is done. So let's say training done. And we can actually go ahead and save this features and labels list. And we're going to say np.save. We're going to call this features.npy, and we can pass in features. And we can do np.save labels.npy, and we can pass in the labels. So let's save that and run. Cool. So essentially now the face recognizer is trained and we can now use this. But the problem here is that if we plan to use this face recognizer in another file, we'll have to separately and manually repeat this process, this whole process of adding those images to a list and getting the corresponding labels and then converting that to NumPy arrays and then training all over again. What we could do, and what OpenCV allows us to do, is essentially save this trained model so that we can use it in another file, in another directory, in another part of the world, just by using that particular YAML source file. So we're going to repeat this process again, but the only change that I'm going to do is I'm going to say face recognizer.save, and we're going to give it a path to a YAML source file. So we're going to say face_trained.yaml. So let's repeat this process again. Training's done. And now you'll notice that you have a face_trained.yaml file in this directory, as well as faces, as well as features.npy and labels.npy. So let's actually use this trained model to recognize faces in an image. So let's close this out and create a new file, and we're going to call this face_recognition.py. Very simply, we're going to import NumPy as np and cv2 as cv. We don't need OS anymore because we're not looping over directories. We can essentially create a har_cascade file. So let's do that. Let's go up here, grab this. We can load our features and label array by saying features is equal to np.load features.npy, and we can say labels is equal to np.load, let's call this labels.npy. And we can essentially now read in this face_train.yaml file. So let's go over here. Let's grab this line. And let's say face recognizer.read. And we're going to give it the path to this YAML source file. So face_train.yaml. So that's pretty much all we need. Now we need to get the mapping, so let's grab this list as well. And let's print that there. So that's pretty much all we have to do. So let's create a variable image, and let's set this to cv.imread. Give it a path. Let's grab one from this validation. I have one of Ben Affleck, so let's try this with, grab that, paste that there, and grab maybe, I don't know, this image, grab that, and let's paste that there, and that's a JPG file. And we can convert that image to grayscale, cv.cvt color, pass in the image, cv.color_bgr to gray. So let's display this image. See, color is the person, unidentified person. Let's paste in the gray. So what we're going to do is we're going to first detect the face in the image. So the way we do that is by saying faces_rect is equal to har_cascade dot detect multi-scale, we pass in the gray image, we pass in the scale factor, which is 1.1, give it a minimum neighbors of 4, and we can loop over every face in this faces underscore rect, so for x, y, w, h in faces underscore rect, we can grab the region of interest, so what we're interested in finding, so y to y plus h and x to x plus h. And now we can predict using this face recognizer. So we get the label and a confidence value, and we say face recognizer.predict, and we predict on this faces underscore ROI. Let's print, let's call this label is equal to label with confidence of confidence. And since we're using numerical values, we can probably say people of label. Okay, and we can essentially, what we can do is we can put some text on this image just to show us what's really going on. We can put this on the image. We can create a string, a variable of people of label, so the person involved in that image, give it an origin, or let's say 10, let's say 20 by 20. Give it a font face of cv.font underscore Hershey underscore complex. Give it a font scale of 1.0. Give it a color of 0,255, 0, and give it a thickness of 2. And we can draw a rectangle over the image, over the face. And this is, we draw this over the image. We give it x to y and x plus w, y plus h. We give it a color of 0,255, 0, and we can give it a thickness of 2. So with that done, we can finally display this image, called as the detected base, and we can pass in the image. And finally, we can do a cv.wait key 0. So let's save and see what we get. So Python face underscore recognition.py. Cannot be allowed to allow pickle is equal to false. Oh gosh, where's that? We probably don't need this anymore, so let's comment that out. If you wanted to use these again, you could essentially use mp.load. Since the data types are objects, you can basically say allow pickle is equal to true. That's essentially it, but we're not going to use this, so let's comment that out. Save. And okay, we get Ben Affleck with a confidence of 60%. So that's pretty good. 60% is good given the fact that we only trained this recognizer on 100 images. So let's try this with another image of Ben Affleck. Maybe this image. Copy that, go right across here and paste that there. Okay, this again is Ben Affleck with a confidence of 94%. Pretty good. Let's go back. Let's go maybe to another person. Let's go to Madonna. Let's first grab this. It's a pain really, but maybe let's change this to Madonna. And let's grab, I don't know, this person. I'm not sure whether it will detect a face because of the hair, but let's paste that anyway. Now this is where you'll find that OpenCV's face recognizer, built-in face recognizer, is not the best. It currently detects that this person in the image is actually Jerry Seinfeld, And that too with a confidence of 110%. Maybe there's an error somewhere. I'm not sure why that went to 111, but I'm pretty sure there's an error somewhere. But essentially, this is where the discrepancies lie. It's not the best, so it's not going to give you accurate results. So let's try this with another image. Let's go back to maybe, I don't know, this image. Copy that. Let's go, paste that there. Okay, this is Madonna with the confidence of 96.8%. Okay, let's move on to Elton John. Last time I had problems with Elton John, given the fact that he looked pretty similar to Ben Affleck for some reason. Copy that, change that to Elton_John, and print that. Okay, Elton John with a confidence of 67%. Pretty good. Okay, so not bad. This is more accurate than what I predicted. Before filming this video, I did a couple of trial runs and I got varied results. For example, Elton John was continually detected as Jerry Seinfeld or Ben Affleck. Madonna was detected as Ben Affleck. Ben Affleck was detected as Mindy Kaling. Mindy Kaling was detected as Elton John, and a whole bunch of weird results. So I guess that we did something right. I must have done something wrong in the trial runs, but hey, we get good results, and that's pretty good. Now, I'm not sure why that gave a confidence of 111%. Maybe there's an error somewhere with the training set, but I guess for the most part you can ignore that, given the fact that we get pretty good results. So that's pretty much it for this video. We discussed face recognition in OpenCV. We essentially built a features list and a labels list, and we trained a recognizer on those two lists, and we saved a model as a YAML source file. In another file, we essentially read in that saved model, saved YAML source file, and we essentially made predictions on an image. And so in the next video, which will actually be the last video in this course, we will discuss how to build a deep learning model to detect and classify between 10 Simpson characters. So if you have any questions, comments, concerns, whatever, leave them in the comments below. Otherwise, I'll see you in the next video. Hey everyone, and welcome to the last video in this Python and OpenCV course. Previously, we've seen how to detect and recognize faces purely in OpenCV, and the results we got were varied. Now, there are a couple of reasons for that. One is the fact that we only had 100 images to train the recognizer on. Now, this is a significantly small number, especially when you're training recognizers and building models. Ideally, you'd want to have at least a couple of thousand images per class. The second reason lies in the fact that we weren't using a deep learning model. Now, as you go deeper into especially computer vision, you will see that there are very few things that can actually beat a deep learning model. So that's what we're going to be doing in this video, building a deep computer vision model to classify between the Simpson characters. Now, generally, OpenCV is used for pre-processing the data, that is, performing some sort of image normalization, mean subtraction, and things like that. But in this video, we're going to be building a very simple model, so we're not going to be using any of those techniques. In fact, we'll only be using the OpenCV library to read in an image and resize them to a particular size before feeding it into the network. Now, don't worry if you've never used or built a deep learning model before. For this video, we'll be using TensorFlow's implementation of Keras. Now, I want to keep this video real simple just so you have an idea of what really goes on in more advanced computer vision projects. And Keras actually comes with a lot of boilerplate code. So if you've never built a deep learning model before, don't worry, Keras will handle that for you. So kind of one of the prerequisites to building a deep learning model is actually having a GPU. Now, a GPU is basically a graphical processing unit that will help speed up the training process of a network. But if you don't have one, again, don't worry, because we'll be using Kaggle, a platform which actually offers free GPUs for us to use. So real simple, before we get started, we'll need a couple of packages installed. So if you haven't already installed Sierra at the beginning of this course, go ahead and do a pip install Sierra. The next package you require is Canero. Now this is a package that I built specifically for deep learning models built with Keras. And this will actually prove surprisingly useful to you if you plan to go deeper into building deep computer vision models. Now installing this package on your system will only make sense if you already have a GPU on your machine. If you don't, then you can basically skip this part. So we can do a pip install Canero. And Canero actually installs TensorFlow by default. So just keep that in mind. So with all the installations out of the way, let's actually move on to the data that we're going to be using. So the dataset that we're going to be using is the Simpsons character dataset that's available on Kaggle. So the actual data that we're interested in lies in the Simpsons_dataset folder. This basically consists of a number of folders with several images inside each subfolder. So Maggie Simpson has about 128 images. Homer Simpson has about 2200 images. Abraham has about 913 images. So essentially what we're going to do is we are going to use these images and feed them into our model to essentially classify between these characters. So first thing we want to do is go to kaggle.com/notebooks, go ahead and create a new notebook. And under advanced settings, make sure that the GPU is selected since we're going to be using a GPU. After that, click create. And we should get a notebook. So we're going to rename this to Simpsons. And another thing I want to do is enable the internet since we're going to be installing a couple of packages over the internet. So to use the Simpsons character dataset in our notebook, you need to go ahead to add data, search for Simpsons. And the first one by Alex Satia should pop up. Go ahead and click add. And we can now use this dataset inside our notebook. So the first thing I want to do is we're going to pip install Sierra and Canero. Now the reason why I'm doing this again is because Kaggle does not come pre-installed with Sierra and Canero. Now I did tell you to install it on your machine, and the reason for that is because you all can work with it and experiment with it. So once that's done, go ahead to a new cell and let's import all the packages that we're going to need. So we're going to import OS, we're going to import Sierra, we're going to import Canero, we're going to import NumPy, ASNP, we're going to import CV2 and CV, and we're going to import GC for a garbage collection. Then next what I want to do is basically when building deep computer vision models, your model expects all your data, all your image data to be of the same size. So since we're working with image data, this size is the image size. So all the data, all the images in our dataset will actually have to be resized to a particular size before we can actually feed that into the network. Now with a lot of experiments, I found that an image size of 80 by 80 works well, especially for this Simpsons dataset. Okay, the next variable we need is the channels. So how many channels do we want in our image? And since we do not require color in our image, we're going to set this to 1, basically grayscale. So run that. What we need next is we're going to say car_path is equal to the base path where all the data, where all the actual data lies. And that is in this Simpsons_dataset. This is the base folder for where all our images are stored in. So we're going to copy this file path and we're going to paste that in there. Cool. So essentially what we're going to be doing now is we're essentially going to grab the top 10 characters which have the most number of images for that class. And the way we're going to do that is we are going to go through every folder inside the Simpsons_dataset, get the number of images that are stored in that dataset, store all of that information inside a dictionary, sort that dictionary in descending order, and then grab the first 10 elements in that dictionary. I hope that made sense. So what we're going to do is we're going to say create an empty dictionary. We're going to say for character in os.list dir car path, we are going to say car_dict of car is equal to length of os.list_dir of os.path.join. We're going to join the car_path with car. So essentially all that we're doing is we're going through every folder, we're grabbing the name of the folder, and we're getting the number of images in that folder, and we're storing all that information inside a dictionary called car_dict. Once that's done, we can actually sort this dictionary in descending order. I'll say descending order. And the way we do that is we say car_dict is equal to cr.sort_dict of car_dict, and we set descending equals to true. And finally, we can print the dictionary that we get. So this is the dictionary that we have. So as you can see, Homer Simpson has the most number of images at close to 2,300. And we go all the way down to Lionel, who has only 3 images in the dataset. So what we're going to do is, now that we have this dictionary, what we're going to do is we are going to grab the names of the first 10 elements in this dictionary and store that in a list, a characters list. So we're going to say characters. So we're going to say characters is equal to an empty list. And we're going to say for I in car_dict, we're going to say characters.append, and we're going to append the name. So we say I of 0. And we say if count is greater than or equal to 10, we can break. And we need to specify a count of 0 and increment that count. Okay, once that's done, let's print what our characters looks like. So we've essentially just grabbed the names of the characters. So with that done, we can actually go ahead and create the training data. And to create a training data is as simple as saying train is equal to cr.preprocess from dir. We pass in the car_path, the characters, the number of channels, the image size, and we say is shuffle equals true. So essentially what this will do is it will go through every folder inside car_path, which is Simpsons_dataset, and we'll look at every element inside characters. So essentially it's going to look for a Homer Simpson inside the Simpsons_dataset. If it finds Homer Simpson, where's Homer Simpson? If it finds Homer Simpson, it's going to go through inside that folder and grab all the images inside that folder and essentially add them to our training set. Now, as you may recall in the previous video, our training set was essentially a list. Each element in that list was another list of the image array and the corresponding label. Now, the label that we had was basically the index of that particular string in the characters list. So that's essentially the same type of mapping that we're going to use. So Homer Simpson's going to have a label of 0, Ned will have a label of 1, Lisa will have a label of 3, and so on. So once that's done, go ahead and run this. Now, basically the progress is displayed to the terminal. If you don't want anything outputted to the terminal, you can basically just set the verbosity to 0. But I'm going to leave things just as it is. Since there are a lot of images inside this dataset, this may take a while depending on how powerful your machine is. So that's done. It took about a minute or so to pre-process our data. So essentially let's essentially try to see how many images there are in this training set. We do that by saying the length of train. And we have 13,811 images inside this training set. So let's actually try to visualize the images that are present in this dataset. So we're going to import matplotlib.pyplot as PLT. we're going to do a plt.figure, and we're going to give it a fig size of 30 by 30. Let's do a plt.imShow. We can pass in the first element in this training set, so 0 and then 0. And we can give it a color map of gray. And we can display this image. Now the reason why I'm not using OpenCV to display this image is because for some reason OpenCV does not display properly in Jupyter Notebook. So that's why we're using matplotlib. So this is basically the image that we get. It's not very legible, but to a machine, this is a valid image. Okay, the next thing we want to do is we want to separate the training set into the features and labels. Right now, the training set basically is a list of 13,811 lists inside it. Inside each of that sublist are two elements, the actual array and the labels itself. So we're going to separate the feature set or the arrays and the labels into separate lists. And the way we do that is by saying feature set and labels is equal to sierra.sep_train. We are going to separate the training set and give it an image size of image size. And that's an equals to. So basically what this is going to do is going to separate the training set into the feature set and labels, and also reshape this feature set into a 4-dimensional tensor so that it can be fed into the model with no restrictions whatsoever. So go ahead and run that. And once that's done, let's actually try to normalize the feature set. So essentially we are going to normalize the data to be in the range of 0, 1. And the reason for this is because if you normalize the data, the network will be able to learn the features much faster than, not normalizing the data. So we're going to say feature set is equal to sierra.normalize, and we're going to pass in feature set. Now we don't have to normalize the labels, but we do need to one-hot encode them. That is, convert them from numerical integers to binary class vectors. And the way we do that is by saying from tensorflow.characters.utils import to _categorical, and we can say labels is equal to categorical, and we can pass in the labels and the number of categories, which is basically the length of this characters list. Cool. So once that's done, we can actually move ahead and try to create our training and validation data. Now don't worry too much if you don't know what these are, but basically the model is going to train on the training data and test itself on the validation data. And we're going to say x_train, x_val, and y_train and y_val is equal to sierra.train val split, and we're going to split the feature set and the labels using a particular validation ratio, which we're going to set as 0.2. So that's basically what we're doing. We're splitting the feature set and the labels into training sets and validation sets with using a particular validation ratio. So 20% of this data will go to the validation set and 80% will go to the training set. Okay, now just to save on some memory, we can actually remove and delete some of the variables that we're not going to be using. So we do that by saying del train, del feature set, del labels, and we can collect this by saying gc.collect. Cool. Now, moving on, we need to create an image data generator. Now, this is basically an image generator that will essentially synthesize new images from already existing images to help introduce some randomness to our network and make it perform better. So we're going to say datagen is equal to canary.generators.image data generator, And this basically instantiates a very simple image generator from the Keras using the Keras library. And once it's done, let's create a training generator by setting this equal to datagen.flow, and we can pass in xtrain and ytrain and give it a batch size equal to batch size. So let's actually create some variables here. Let's set my batch size to 32, and maybe let's train the network for 10 epochs. So once that's done, let's run that. So with that done, we can actually proceed to building our model. So let's call this creating the model. Now, before making this video, I actually tried and tested out a couple of models and found that one actually provided me with the highest level of accuracy. So that's the same model architecture that we're going to be using. So we're going to say model is equal to canary.models.create Simpsons model. We are going to pass in an image size, which is equal to the image size. We're going to say set the number of channels equal to the number of channels. We're going to set the output dimensions to 10, which is basically the length of our characters. Then we can specify a loss, which is equal to binary cross entropy. Then we could set a decay of e to the -6th power. We can set a learning rate equal to 0.001. We can set our momentum of 0.9, and we can set Nesterov to true. So this will essentially create the model using the same architecture I built, and we'll actually compile the model so that we can use it. So go ahead and run this, and we can go ahead and try to print the summary of this model. And so essentially what we have is a functional model, since we're using Keras' functional API. And this essentially has a bunch of layers and about 17 million parameters to train on. So another thing that I want to do is create something called a callbacks list. Now this callbacks list will contain something called a learning rate scheduler that will essentially schedule the learning rate at specific intervals so that our network can essentially train better. So we're going to say callbacks list is equal to learning rate scheduler, and we're going to pass in canary.lr_schedule. And since we're using learning rate schedule, let's go and import. So from TensorFlow.keras.callbacks import learning rate scheduler, and that should about do it. So let's actually go ahead and train the model. So we're going to say training is equal to model.fit. We're going to pass in the train gen. We're going to say steps per epoch is equal to the length of x_train divided by the batch size. We're going to say epochs is equal to epochs. We're going to give it a validation data. Validation data equal to a tuple of x_val and y_val. Then we're going to say validation steps is equal to the length of y_val divided by the batch size. And finally, we can say callbacks is equal to callbacks_list. steps per epoch. That's steps per epoch. And that should begin training. And once that's done, we end up with a baseline accuracy of close to 70%. So here comes the exciting part. We're now going to use OpenCV to test how good our model is. So what we're going to do is we're going to use OpenCV to read in an image at a particular file path, and we're going to pass that to our network and see what the model spits out. So let's go ahead and go to this Simpson test set. So let's go ahead and try to search for all the way down here. Let's look at our characters list, just print that out just to see what characters we trained on. Okay, let's look for Bart Simpson. It's probably a bit irritating, but Simpson's dataset. Okay, we got an image of Bart Simpson, so click this, some random path. Go to test path, set this equal to an R string. And what we're going to do is we're going to say img is equal to cv.imread test_path. And just to display this image, we can use plt.imshow. We can pass in the image, and give it a color map of gray. And we can do a plt.show. Okay, plt.show. And okay, so this is an image of Bart Simpson. So what we're going to do is we are going to create a function called prepare, which will basically prepare our image to be of the same size and shapes and dimensions as the images we used to prepare the model in. So this will take in an image, and what this will do is we'll convert this image to grayscale. So we're going to say img is equal to cv.cvt color, and we're going to pass in the img, and we're going to say cv.color_bgr to gray. We can resize it to our image size. So we're going to say img is equal to cv.resize. We're going to resize the image to be image_size, and we're going to reshape this image. So img is equal to reshape of image. We want to reshape the image to be of image size with channels equal to 1. And we can return image. So let's run that. And let's go down here and let's say predictions is equal to model.predict and prepare image. And we can visualize this predictions. So let's print predictions. And essentially this is what we get. So to print the actual class, what we can do is we can print the characters of np.argmax, and we can say predictions of 0. And let's try to visualize this image. So we can do a plt.imshow. Let's pass in the image and plt.show. Let's grab this and move this down there. Let's run that, yeah. Okay, so this is our image, and right now our model thinks that Bart Simpson is in fact Lisa Simpson. Let's go Lisa Simpson. Okay, let's try another image. Let's try probably this image. This Bart Simpson 28. Let's go up there. And maybe change that to 8. Run that. This is Bart Simpson. Let's run this and this, and again we get Lisa Simpson. So let's try with a different image. Yeah, we did Charles Montgomery. So copy this. all the way down there. Set there. Run. And we get Charles. Predict. And we get Van Houten. Okay, definitely not the best model that we could have asked for, but hey, this is our model. Right now, this currently has a baseline accuracy of 70%, although I would have liked it to go to at least 85%. In my tests, it had gone close to 92%. I'm not sure exactly why this went to 70%, but again, this is to be expected since building deep computer vision models is a bit of an art and it takes time to figure out what's the best model for your project. So that's it for this Python and OpenCV course. This course was basically kind of a general introduction to OpenCV and what it can do. Now of course, we've only just scraped the surface, and really there's a whole new world of computer vision out there. Now, while we obviously can't cover every single thing that OpenCV can do, I've tried my best to teach you what's relevant today in computer vision. And really, one of its more interesting parts, building deep learning models, which is in fact where the future is. Self-driving vehicles, medical diagnosis, and tons of other things that computer vision is changing the world in. So all the code and material that was discussed throughout this course is available on my GitHub page, and the link to this page will be in the description below. And just before we close, I do want to mention that although I did recommend you install Sierra in the beginning, we barely use it throughout the course. Now, it's probably not going to make sense to you right now, but if you plan to go deeper into computer vision, into building computer vision models, Sierra will actually prove to be a powerful package for you. It has a lot of helper functions to do just about anything. Now, I'm constantly updating this repository, and if you want to contribute to these efforts, definitely do that. You can set a pull request with your changes, and if it's helpful, it will be merged into the official codebase and you'll be added as a contributor. If you're into building deep learning models with Keras, then Canary will be useful to you. But again, for the most part, it's usually Sierra that you'll be using. So anyway, with that said, I think I'll close up this course. If this course helped you in any way and got you more interested in computer vision, then definitely like this video, subscribe to my channel, as I'll be putting up useful videos on Python, computer vision, and deep learning. So I guess that's it. I hope you enjoyed this course, and I'll see you in another video.